Hello there and welcome to Physics with William. Where curiosity slows its breathing a little, science becomes something you can settle into, and even the strangest corners of the universe can feel calm enough to visit at the end of a long day. Tonight, I want to begin with a question that sounds almost too simple to be worth asking. The sort of thing that could arrive in your mind while lifting a coffee mug, turning over a stone, or absent-mindedly weighing an orange in your palm at the kitchen counter. What is the heaviest possible object that could still fit in your hand? It is such a small question on the surface, almost ordinary. You can imagine asking it half-jokingly while standing in a hardware shop or while picking up something dense and unexpectedly solid and thinking, goodness, that is heavier than it has any right to be. But that is often how physics begins, not with fireworks, not with grand declarations about the nature of reality. It begins with a quiet irritation, or a tiny surprise, or a question that seems almost silly until you follow it one step farther than usual. Because once you do ask what is the heaviest thing you could hold, you very quickly discover that you're not really asking about size at all. You're asking about density, about how much matter can be packed into how little space, about what happens when ordinary substances are squeezed far beyond the tidy limits of daily life, and then, before long, you are standing at the edge of white dwarfs and neutron stars and black holes, all because your hand, humble and familiar as it is, turned out to be a doorway. Before we wander too far into that doorway, I would love to know where in the world you are listening from tonight, and what sort of hour this finds you in. Is it late, and the house has begun to quiet down? Is it early, with the day only just beginning to gather itself? Perhaps you're listening under a blanket, perhaps through headphones on a train, perhaps with a cup of tea going lukewarm beside you because attention has gone elsewhere, as it tends to do when space and gravity arrive in the conversation. There is something fitting, I think, about asking where you are while talking about an object in your hand. The scale is so personal, so immediate, not a galaxy far away, not some abstraction in a textbook, but your own palm, your own grip, your own sense of weight. And if this kind of slow wandering through physics is the sort of thing that helps you unwind, or keeps you company, or gives your thoughts somewhere gentle to rest, then a like or a subscription would be warmly appreciated. It helps this quiet little corner find the people who might enjoy spending an evening wondering how much mass could sit, just barely, in the curve of a human hand, which, to be honest, is not a sentence most channels get to say very often. So let us begin there, with the hand itself, not as a poetic object, not as a philosophical symbol, but as a rather practical measuring device. Your hand is not especially large. It is not especially strong either, compared with cranes or presses, or even the more determined varieties of shopping bag. And yet it is a marvellous thing for judging the world. You know when something feels comfortable to hold, when it feels awkward, when it feels fragile, when it feels surprisingly dense. A tennis ball and a rock can take up roughly similar space, and yet one belongs in a game and the other belongs in a sling or a garden. A loaf of bread fills your hands without really burdening them. A bag of sugar, much smaller, announces itself immediately. Size alone tells you very little. Weight alone tells you only a bit more. What matters is the relationship between the two. That relationship is so familiar that we navigate it constantly without naming it. You pick up a cardboard box and expect one thing, then discover someone has packed books into it and suddenly your knees have opinions. You lift a ceramic mug and a plastic cup of the same size, and one feels substantial while the other feels almost theatrical, as if it is pretending to be a proper container. We live with density all the time. We simply do not usually stop to look at it directly. Suppose, then, that someone handed you a ball small enough to fit neatly in your palm, perhaps the size of an apple, perhaps even a little smaller, and asked you to guess its weight. You would likely reach first for ordinary experience. Is it made of wood, plastic, stone, iron? Is it hollow? Is it solid? Your mind would search the catalogue of things it already knows. And that catalogue works well enough for most of life, because the matter around us behaves in reassuringly consistent ways. Wood is lighter than metal. Aluminum is lighter than steel. Lead is one of those substances everyone learns to associate with heaviness, even if most of us do not spend our afternoons carrying chunks of it around. Already, though, there is something interesting hiding in that list. Some materials are much denser than others, but there are limits to how dense ordinary matter tends to be in daily life. You can find substances that feel impressively heavy for their size. There are metals that make the hand pause and the wrist take notice. Tungsten is a famous example, the sort of material that makes people smile the first time they hold it because the brain has guessed wrong. A small piece can feel oddly serious, like it belongs to a larger object that has somehow been folded down into a compact, stubborn little shape. Osmium is even denser, though less likely to appear casually in your pocket unless you have a very unusual pocket and even more unusual hobbies. What is delightful about these materials is that they give us a first glimpse of the whole question. They show that a hand-sized object can become shockingly heavy, long before it becomes fantastical. You do not need stars or collapsed matter to surprise a person. Sometimes a dense metal cylinder will do the job nicely. The hand expects volume to correspond roughly with weight, and when that expectation is violated even a little, you feel the gears turning in your mind. You begin to realize that the world allows more mass in a small space than intuition first suggested. But then the deeper question arrives. If tungsten is dense, and osmium is denser still, is there a ceiling? Is there some final earthly material beyond which matter simply cannot be packed any tighter? Or is the periodic table only an opening act, a polite introduction before physics becomes much stranger and much less concerned with what a chemist would recognize as normal substance? This is where the question stops being about shopping for very serious paperweights and starts becoming something else entirely. Because ordinary materials, however dense, are still built from atoms that maintain a certain structure. They are not just featureless lumps of matter, they are mostly empty space in a sense that sounds absurd until you remember what atoms are like. Tiny nuclei, electrons occupying regions around them, distances that are enormous relative to the scale of the nucleus itself. Matter feels solid to us not because it is packed edge to edge like bricks in a wall, but because of the rules governing those particles, the electromagnetic forces that keep atoms from simply sliding through one another as if nothing were there. Your hand pressing against a table feels like solid against solid, but on the deepest level it is a kind of structured refusal. Matter maintaining boundaries. That may sound slightly odd for a sleepy evening thought, but it matters here because it means everyday density is not the end of compression. Not even close. What you call a dense metal is, from a more extreme point of view, still roomy, still spacious, still living comfortably under the ordinary arrangements that atoms prefer, and that preference is important. Matter does not generally enjoy being compressed indefinitely. It resists. Push atoms together, and the electrons and nuclei begin to object in increasingly dramatic ways. The object may deform, it may heat up, it may change phase, it may break. At some point, you're no longer simply making a denser version of the same thing. You're forcing matter into new regimes where the familiar rules of chemistry begin to lose authority. This is one of the quiet thrills of the question. You start with a hand, and before long you are confronting the fact that matter has layers of behaviour. There is the level we know from furniture, tools, cookware, rocks, coins and door handles. Then there is the level reached in extraordinary pressure, where atoms are crowded so hard that their ordinary identities begin to fail them. And beyond that there are stellar remnants, places where matter is no longer organised in anything like the way it is in the room around you now. Yet before we rush off towards stars, it is worth lingering with the hand a little longer, because it sets the scale in a useful way. A hand-sized object is small enough to feel intimate. You can imagine holding it, turning it over, feeling its texture, if it has one, testing its heft. There is something almost mischievous about asking how much mass could hide inside that small familiar volume. A mountain is heavy, yes, but that teaches us very little. Its heaviness is spread out honestly, almost generously, over its enormous size. A tiny object that weighs absurdly much is more unsettling. It seems to violate a kind of social contract with the senses, and we are very sensitive to those violations. The body notices quickly when expectations fail. Lift an empty suitcase you thought was full, and it leaps upward like a stage prop. Lift a full suitcase you assumed was empty, and your spine writes a formal complaint. That mismatch between prediction and reality is not just funny. It is educational. It reveals that your brain is always making physical models, always anticipating mass from shape and material and past experience. Physics is happening in the nervous system all the time, whether or not we call it by name. So now imagine training that instinct far beyond the everyday. Imagine asking not only what material is densest in the ordinary sense, but what matter could become if compression kept going, if all the airy spacing inside atoms were reduced, if gravity itself, under conditions far beyond Earth, became the great compressor, if stars, after exhausting their ordinary lives, left behind remnants so compact that the very concept of a hand-sized object begins to wobble. A curious thing happens at this point in the story. Weight and danger begin to merge. Up to a certain stage, asking what is the heaviest thing you can hold is just an interesting physical puzzle. Beyond that stage, it becomes slightly less of a holding exercise and slightly more of a survival issue. Because mass does not merely sit there quietly when enough of it is packed into a small region. It brings gravity with it. Not the mild, courteous kind that keeps your slippers on the floor, but the sort that starts rearranging the neighbourhood. There comes a threshold where the question is no longer whether it fits in your hand, but whether your hand, your arm, the floor beneath you, and quite a lot of earth in the vicinity would care to remain organised in their current form. That, in a way, is the true shape of tonight's question. Not just heaviness, but the consequences of density. A hand-sized object made of a dense metal is still just an object. Heavy, certainly. Unwise to drop on your foot, absolutely. But still a thing governed by the usual manners of matter. Once you move into the territory of stellar matter, you are dealing with something that carries the memory of enormous pressure. Something born in environments where gravity has squeezed the ordinary life out of atoms and demanded a harsher arrangement. It is remarkable, really, that the universe permits such arrangements at all. That matter can exist as rock and rain and bread and brass, but also as the remnants of dead stars, compressed into states so extreme that our daily vocabulary begins to fail. We are used to thinking of matter as a menu of materials: wood, glass, iron, water. Yet under sufficient pressure, matter ceases to be a menu and becomes a drama. The actors lose their costumes. The stage itself changes. Perhaps that is why questions like this are so satisfying. They let us begin with something tactile and end somewhere almost unimaginable. You do not need to start by asking what happens inside a neutron star. You can start by holding a coin and noticing that it feels denser than the napkin beneath it. From there, step by step, the same logic carries you outward. If this material is denser than that one, then what is the densest ordinary material? And if ordinary materials still contain a great deal of internal space, then what happens when that space is forced shut? And if gravity can do that to matter in stars, then what would a tiny sample be like? And if you keep going, can there be so much mass in so little volume that not even light can get away? All of that from a human hand, which is not bad as gateways go. There is also something quietly humbling in using the hand as the reference point. Hands build things, measure things, hold things. They represent our scale, our size, our way of meeting the world. To ask what could fit in one is to measure the universe against the body. We do this constantly, even in language. A handful, a palm-sized stone, within reach. Too heavy to carry, easy to lift. The body is the first laboratory. Before there were particle accelerators and space telescopes, there were hands testing weight, texture, resistance, temperature. We learned the world by touching it, pushing it, lifting it, dropping it, and occasionally regretting those decisions. And so, the question we are following tonight is almost ancient in spirit. Even though its destination is modern astrophysics, how much can a small thing contain? How heavy can it become before smallness itself stops being an innocent property and starts becoming something profound? The first answers, as we move forward, will still belong to the familiar world. Dense metals, solid matter. Things that could, in principle, exist on a workbench without rewriting the laws of your household. That is where intuition still has some footing, but intuition does not keep that footing for long. Soon enough, the matter in question will be matter that no longer behaves like the stuff around you now. Matter stripped of its normal atomic character, matter whose density is so extreme that to imagine a hand-sized amount is to imagine a piece of a dead star brought impossibly close. And even that, astonishingly, is not the end, because there is a final limit hidden in the question, a point where increasing mass in a small enough region ceases to produce merely a denser object, and instead creates a black hole. At that point, the heaviest possible thing that fits in your hand becomes a stranger idea altogether. Not a super heavy ball, not a miraculous metal, not a tiny star fragment in any practical sense, but an object whose gravity has become so concentrated that the very notion of holding it starts to sound like the sort of plan one should reconsider after a good night's sleep. So that is where we are going. From the reassuring heft of earthly materials to the crushed remains of stars, and onward to the edge where matter gives way to gravity as the main character. We will begin gently with the densest substances that still belong to chemistry and engineering, the kinds of things that can surprise the hand without destroying the room, and from there we will keep asking the same simple question, only more seriously each time. If it still fits, how heavy could it be? If it still fits, what would it do? If it still fits, is it even matter anymore in the way we usually mean the word? That is when the real fun begins, because the answer is not just a number. It is a tour through the structure of matter itself, from ordinary atoms to the point where ordinary matter stops behaving like matter at all. When we ask how heavy a small thing can be, we are really asking two questions at once, even if it does not sound that way at first. One question is practical. How much weight could a human hand actually lift if the object were compact enough to grip comfortably? The other is physical. How much mass can be packed into a small volume before the material itself becomes something unusual? Those are not quite the same question, and the difference between them matters. A hand can only manage so much before wrists complain. Fingers lose confidence, and gravity wins the argument. Matter, on the other hand, has its own story. It can be arranged in ways that make a small object surprisingly heavy, long before it becomes impossible to hold in any ordinary sense. That distinction is worth sitting with for a moment because the word heavy can mislead us. In daily life, when we say something is heavy, we usually mean it feels heavy to us, it strains muscles, it tugs downward, it makes us adjust posture without thinking. But in physics, heaviness is not really about inconvenience. It is about mass and gravity, and how much stuff there is packed into a certain amount of space. A bowling ball feels heavy because it contains a good deal of mass in a fairly modest volume. A pillow does not, despite being large enough to occupy much more room on the sofa and much more emotional importance in a bedtime routine. This is why small, heavy things are so interesting. Large, heavy things do not surprise us very much. A car is heavy, a refrigerator is heavy, a piano is heavy, and it has been causing domestic logistical crises for generations. None of these are mysterious because their size prepares us for their mass. But a small object that feels unexpectedly weighty can be genuinely startling. It slips past the brain's usual predictions. You look at it and imagine one effort, then lift it and discover that your body had planned poorly. That little mismatch between expectation and reality is one of the first places where density becomes visible to the senses. There is a simple reason the brain gets caught out. Most of the time, size and weight do roughly travel together. Bigger things often do weigh more. Not always, but often enough that your nervous system has learned the pattern and uses it constantly. It is efficient. It would be exhausting to calculate the mass of every mug, bag, book, fruit, or chair before touching it. So instead, the brain makes a fast estimate from shape, size, and whatever clues it can gather about the material. Usually that is good enough. Sometimes it is hilariously wrong. Think of a small decorative object made of cast iron or bronze. It may be no larger than a plum, yet when you pick it up it feels oddly committed to the floor, as though it has personal views about being moved. Or consider a compact camera lens dense with glass and metal compared with a much larger plastic toy. One occupies less space but insists on much more respect from your hand. This is not magic. It is simply that matter can vary quite a lot in how much mass it contains per unit of volume, and our intuitions are only approximate guides. Even in the ordinary world there is a significant spread. A block of dry wood and a block of stone of the same size are very different experiences. A block of aluminum and a block of lead, same story. If you are given two objects that occupy the same amount of space, but one is made of a less dense material and the other of a more dense one, the difference can be dramatic. That is already enough to show that small things can become impressively heavy without requiring any extreme physics. The world of ordinary matter still has plenty of room for surprise, but there is another layer here that makes the question more interesting than a simple ranking of materials. When we say a thing is small, what do we really mean? Small enough to fit in your hand is not a precise scientific category. Hands differ. A child can cradle something that an adult can palm easily. One person can grip a smooth sphere comfortably, while another finds it awkward. A cube feels different from a cylinder. A dense object with a handle may be easier to carry than a denser object with no good place to hold. So even before physics enters, anatomy and ergonomics are already having their say. That makes the practical side of the question slightly mischievous. If the object is too heavy, the issue may not be whether it fits in your hand, but whether your hand still counts as being in charge of the situation. You might be able to touch it. You might even get your fingers around it. But lifting it cleanly, controlling it, and setting it down without meeting the floor faster than expected are different matters. A dense enough hand-sized object could be an object you can technically hold for a moment, in the same sense that one can technically carry too many grocery bags at once. The laws of physics allow it. The tendons remain unconvinced. Still, for now, it helps to separate human strength from the deeper issue of how much mass a small object can contain. Imagine, just as a thought experiment, that you're not limited by comfort or common sense. Imagine your hand is merely the measure of size, not the measure of what your bones are willing to tolerate. We're not asking what you ought to carry through a parking lot. We're asking how far smallness and heaviness can coexist. The answer begins with something very plain. Heavy and small go together when density is high. That seems almost too obvious to be worth saying, but it is the key that unlocks everything that follows. If you double the size of an object in all directions while keeping the material the same, the mass rises much faster than our simple visual intuition tends to appreciate. And if you keep the size fixed but change the material to something denser, mass increases without any obvious outward transformation. The object looks the same size. It just acquires a much more serious relationship with gravity. This is one reason dense objects feel a bit uncanny. Their external appearance does not advertise their internal commitment. A large foam ball and a metal sphere of the same diameter do not differ in shape, only in what fills that shape. Yet one behaves like a prop, and the other like a statement. The difference is hidden inside the material, not revealed by the outline. Much of physics is like this: outward simplicity, inward complication. There is also an educational pleasure in small, heavy objects because they reveal how little of ordinary matter is really solid in the naive sense. That may sound strange. A table feels solid. A wall feels solid. A metal weight feels very solid indeed, especially if dropped. But the solidity we experience is not the same as maximum compactness. Atoms maintain spacing. Electrons occupy allowed regions. Nuclei sit at the centre of those arrangements, and almost all the actual mass lies in a tiny core compared with the total size of the atom. Everyday materials are structured, stable and resistant, but they are not packed to the ultimate limit, not even remotely. That's why the question has such reach. Once you notice that ordinary matter already allows substantial variation in density, you start to wonder how much further that could go. If atoms are mostly a matter of arrangement, then different arrangements should permit very different amounts of mass in the same volume. And if the arrangement itself breaks down under sufficient pressure, then all bets become negotiable. Before we travel that far, it helps to appreciate just how impressive even ordinary densities can be. Suppose you had a cube small enough to sit comfortably in your palm. If it were made of a light material, it might feel almost trivial. If it were made of a dense metal, it could feel alarmingly important. The volume has not changed. Only the amount of mass inside that volume has changed. Your hand learns very quickly that volume is not the boss. This lesson becomes even clearer with metals, because metals are, in a sense, matter that has already agreed to a relatively compact arrangement compared with many everyday materials. Their atoms are packed in organized structures. Their electrons behave in ways that support bonding and conductivity. Their density can be high enough that even modest pieces feel more substantial than their size suggests. This is why a small bar of certain metals can seem more dramatic than a much larger household object. The hand notices not the visual footprint, but the resistance to being accelerated upward. There is something almost comic about how quickly this can humble intuition. A person may confidently reach for a compact metal sample, assuming it will be easy to lift, only to discover that it has the attitude of something much larger. It is the physical equivalent of meeting a very short person with the voice of a cathedral organ. The scale seems to promise one thing and then delivers another. Dense matter is full of that kind of contradiction. Now, if we stay within the familiar world, there are reasonable upper ranges for how heavy a hand-sized object might become. Not because nature imposes a mysterious everyday limit, but because common materials occupy a certain band of densities. Some substances are light because their atoms are arranged loosely or made from lighter elements. Others are heavy because the atoms themselves are more massive and sit closer together. Once you reach the densest ordinary elements and compounds, you are already near the ceiling of what chemistry routinely allows. A hand-sized object made from such materials can become heavy enough to impress, strain, and possibly bruise a toe, but it still remains comprehensible as an object. This point matters because people often underestimate how much can happen before anything exotic enters the room. You do not need star matter to create a wildly heavy object for its size. Even within the periodic table, nature offers materials that can make a small object feel almost unreasonable. That is the first genuine answer to our question. Small things can be surprisingly heavy simply because the everyday world contains materials with very different internal packing and very different atomic masses. Yet as interesting as that is, it is still only the beginning. Because once you ask why there should be any upper bound at all, you're no longer doing household intuition. You're doing fundamental physics. Why should atoms keep their distance the way they do? Why should ordinary matter settle into the densities we find on Earth? Could you not just squeeze it harder, make the atom share less room? Press the structure down until the same hand-sized object contains much more mass than chemistry would normally permit. The short answer is yes, but only by leaving the ordinary world behind. Under enough pressure, matter can be forced into states that do not exist naturally on the surface of our planet. The deeper answer is that the resistance of matter to compression is one of the main characters in the story of stars. Gravity pulls inward, matter pushes back in various ways. For normal objects, electromagnetic interactions and atomic structure do the work. For more extreme objects, other forms of pressure take over, and if gravity becomes strong enough, it can push matter into arrangements so dense that our usual concept of material almost stops being useful. It is tempting to think of this as simply more squeezing, as though matter were a sponge and the universe merely had very firm hands. But the reality is more dramatic than that. closer matter is pressed, the more the rules change. Electrons resist being crowded into the same states. Nuclei come closer than they ever do in ordinary solids. Heat, pressure, and quantum rules all begin to matter in ways that have no real counterpart in the kitchen, the garage, or the garden shed. The object may still be small in size, but the physics inside it becomes something you would never infer by looking. That is one reason the hand is such a useful anchor. It reminds us how deceptive appearance can be. A hand-sized object could be harmless foam, dense metal, or something so extreme that holding it would cease to be a sensible activity in any conventional meaning of the word. The shape tells you almost nothing. The interior decides everything. It is also worth noting that heaviness is never just about the object alone. Gravity is part of the conversation. A kilogram on Earth feels different from a kilogram on the Moon because the pull downward changes. The mass is the same, but the weight you feel is different. That might seem like a technical distinction, yet it becomes important later, because as objects become denser and more massive, they begin to contribute more of their own gravity to the situation. An ordinary metal ball is heavy because Earth pulls on it. A sufficiently extreme object starts becoming remarkable not only because Earth pulls on it, but because it pulls back on everything around it in a more noticeable way. For now, ordinary hand-sized objects do not do much of that. They sit there politely and let the planet handle the downward business. But the idea is already lurking. There is a threshold beyond which a small object is not just passively heavy. It becomes actively influential. It disturbs its surroundings. It changes what nearby matter would do. That is when the question becomes much more than a question about lifting strength. Before we reach those astonishing cases, though, it helps to stay grounded in the present step. How heavy can small things be? Much heavier than size alone would suggest. Heavier enough that intuition starts to fail. Heavier enough that the hand teaches you the lesson directly. A small object can carry surprising mass if the material inside it is packed efficiently. That is the basic rule. The rest of the journey is just the universe showing us how far that principle can be taken. And nature, as it turns out, is willing to take it a very long way. First through the densest materials that still belong to the ordinary world of atoms, metals and chemistry. Then through matter crushed beyond ordinary atomic structure. Then through stellar remnants whose density is so extreme that a tiny amount would outweigh mountains. And finally to the point where stuffing enough mass into a small enough region stops producing an object in the familiar sense and starts producing a black hole. But before the stars start intruding, it makes sense to pause at the edge of the ordinary world and ask a more concrete question. If we search among the substances we actually know on Earth, the real materials of furnaces and laboratories and very serious metal samples, which ones come closest to the limit of everyday density? Which materials make the strongest claim to being the heaviest things, volume for volume, that still belong to normal matter? That is where the next step becomes especially satisfying, because now the question leaves the general and becomes specific. It is no longer about whether small things can be heavy. It is about which small things exactly are the reigning champions of the ordinary world and why they feel so strangely committed to staying in your hand once you pick them up. Now that the question has narrowed from how heavy can a small thing be to which ordinary materials come closest to the limit, the ground under our feet becomes much more familiar. We are no longer talking about the crushed remains of stars or matter under impossible pressures. We are talking about the substances that belong to the everyday universe of mines and foundries and laboratories. Dense matter on Earth is still matter in the ordinary sense. It still has atoms arranged in structures that chemistry would recognize. It still behaves like a material you could in principle cut, shape, weigh, and place on a table. Though in some cases you might want a rather sturdy table, and a good reason for owning it. Most people, if asked to name the heaviest ordinary material, would probably say lead. Lead has earned that reputation honestly enough. It is familiar. It is used where weight matters. It feels serious in the hand. It has been part of human life for a very long time, and language has helped keep the association alive. A lead weight sounds like the default answer to heaviness, in the same way that a feather sounds like the default answer to lightness. But lead is not actually the densest ordinary matter we encounter on Earth, not even particularly close to the very top. It is just one of the more famous members of a much heavier club. That club is filled mostly with very heavy metals, the sort of elements whose atoms have large nuclei and whose structures allow those atoms to sit together with impressive efficiency. Gold belongs there. Platinum belongs there. Tungsten belongs there. Iridium belongs there. Osmium belongs there too, and in many lists it is the one that takes the crown, though in practice the race at the top is so close that iridium is always nearby, like a rival in the final meters of a long race who refuses to give the commentators an easy evening. This is where density starts to become more interesting than weight alone. A thing is not dense simply because its atoms are made from heavy ingredients. That helps, certainly, but it is not the full story. Density depends on two facts working together. First, the atoms themselves need to carry a lot of mass. Second, they need to be arranged in a way that does not waste much space. If the atoms are heavy but arranged loosely, the material may still be less dense than something made of slightly lighter atoms packed more tightly. So the densest matter on Earth is not merely made of heavy atoms, it is made of heavy atoms that sit together very efficiently. That combination is why the usual champions are found near the heavy end of the periodic table. Their nuclei contain many protons and neutrons, which means each atom carries a lot of mass. At the same time, the electrons surrounding those nuclei settle into patterns that allow the atoms to form tightly packed solid structures. The result is a material that contains a remarkable amount of mass in a modest amount of space. The eye sees a lump of metal. The hand feels something closer to an argument. Osmium is the name that often comes up first in this conversation, and with good reason. It is a hard, bluish metal, not particularly famous outside chemistry and physics circles, but quietly extraordinary in just how much mass it can store in a given volume. It is dense enough that a piece no larger than a small fruit would feel almost absurdly heavy. The surprise would not come from size. It would come from the mismatch between size and effort. The object would not look like it should demand that much respect from your wrist, and yet it would. Iridium lives in almost the same territory. It is similarly dense, similarly heavy for its size, and similarly prone to making people revise their intuitions. In fact, for practical purposes, the difference between osmium and iridium is so slight that the exact ordering can depend on how carefully you measure, what sample purity you assume, and what temperature the material happens to be at. This is not the kind of rivalry that produces dramatic shouting. It is more the quiet scientific kind, where two elements sit nearly tied at the summit while everyone else nods solemnly and checks the decimals. Then there is tungsten, which holds a special place in this story because it combines very high density with a kind of practical visibility. More people are likely to encounter tungsten than osmium or iridium, at least in discussions of dense objects, because tungsten is useful. It is strong, heat-resistant, and far less exotic in industrial life. A compact block of tungsten can feel wonderfully wrong in the hand, as if someone has taken the weight of a much larger object and folded it into a smaller shape just to be mischievous. If you wanted to demonstrate density to someone without involving dangerous chemistry or a very unusual jewellery box, tungsten would be an excellent accomplice. Gold also deserves a moment here, not only because it is dense, but because many people have actually felt that density without thinking much about it. A gold bar, even a relatively small one, carries a famous kind of authority. It is not just valuable in the cultural sense, it feels substantial in a direct physical way. It settles into the hand with a seriousness that lighter materials cannot imitate. There is a reason gold has such a powerful reputation, even apart from economics and ornament. It does not merely shine, it weighs. Platinum is similar in that respect. Dense, heavy, unmistakably metallic, it reminds us that some of the ordinary champions of density are also the materials we attach prestige to, There is something slightly amusing about that. Humans often equate value with scarcity, beauty, or social meaning. But dense, noble metals also deliver a very literal bodily experience of substance. They feel important because, in a simple physical sense, they are. By contrast, some materials are heavy by reputation more than by actual density ranking. Lead, as mentioned, is one of these. It is dense enough to be useful for shielding and ballast and many other jobs where heaviness helps. But if you place lead alongside the true champions of ordinary density, it begins to look a little less unbeatable. It is still a respectable contender. It simply is not the reigning monarch it is sometimes imagined to be. Mercury is another interesting case because it reminds us that density is not tied to being solid. Mercury is a liquid metal, and quite a dense one. To see a liquid behave with such weight can be faintly unsettling. We're used to liquids sloshing and yielding and seeming somehow less committed to their own presence than solids do. Mercury ignores that expectation. It pours like a liquid but carries itself with the confidence of something heavier than many solids. It is one more example of how our instincts are shaped not by pure physical truth, but by what we usually encounter. If all of this feels like a parade of names, the deeper point is simple. The densest matter we meet on Earth is ordinary matter at the extreme end of ordinary possibilities. It is what chemistry and atomic structure can do when given very heavy elements and efficient packing. That phrase matters. Ordinary possibilities. Because even at their densest, these materials are still made of atoms with electron clouds and nuclei. They are still subject to the same broad rules that govern the rest of the material world. They are impressive, but they are not yet strange in the astrophysical sense. To understand why they stop where they do, it helps to look a little more closely at what an atom actually is. We often speak of atoms as though they were tiny hard balls, the little building blocks from which everything is made. That picture is useful at a very elementary level, but it can also mislead. Atoms are not miniature billiard balls packed edge to edge. They have structure. The nucleus is tiny relative to the total size of the atom. The electrons occupy allowed regions around that nucleus. The atom, in a certain sense, is mostly arrangement. Its apparent size comes less from the nucleus and more from the space claimed by its electrons, and the rules that prevent those electrons from all collapsing inward, or overlapping however they please. This means even the densest ordinary metal is not dense because matter has been compressed to its final limit. It is dense because atoms of a certain sort have settled into a very compact but still normal structure. There is still a lot of room compared with what nature can achieve under truly crushing pressure. Everyday dense matter is impressive only when judged against the rest of daily life. Judged against white dwarfs or neutron stars, it looks almost spacious. That contrast is one of the most important in the whole journey. A block of osmium can feel astonishing in your hand, but from the perspective of extreme astrophysics, it is still a rather airy arrangement. It still contains atoms with their familiar identities intact. Electrons still belong to atoms in the ordinary way. Nuclei are still separated by distances that would seem luxurious in a dead star. So when we call osmium or iridium the densest matter we meet on Earth, we are really saying they represent the top end of what undisturbed atomic matter naturally offers us at the surface of our planet. There are, of course, ways to squeeze matter harder for a time. Laboratories can subject materials to immense pressures. Shock waves can compress substances transiently. The deep interior of planets contains matter under far greater pressure than anything lying casually on the ground outside. Iron in the Earth's core exists under conditions unlike those in a workshop or a museum display case. But when we speak of matter we meet on Earth in any familiar sense, we mean substances that can exist stably in our environment and be handled, measured and discussed without having to first recreate the centre of a planet or the aftermath of a violent impact. This keeps the focus exactly where it belongs, not on every possible pressure state a laboratory might briefly produce, but on the materials that represent the upper edge of ordinary density in the world we inhabit. And there is something satisfying about that edge. It tells us chemistry has real limits. You can move from wood to stone to steel to lead to gold to tungsten and beyond, feeling matter become steadily more compact and more serious, but eventually you arrive at a ceiling set by the nature of atoms themselves. Past that point, if you want something much denser, you're no longer shopping among materials, you're changing the rules of matter. That is also why dense metals often feel almost educational the first time a person handles them. They provide a bodily lesson in hidden structure. Two objects can look similar in size and shape yet differ enormously in mass because one is mostly lighter atoms or more loosely arranged atoms, while the other is built from heavier nuclei packed with unusual efficiency. The eye does not see atomic packing. The hand does, indirectly. It feels the consequence even if it cannot name the cause. There is a nice humility in that. Our senses are useful, but they are not complete. We can look at a small tungsten cube and think it ought to be manageable, then lift it and discover that our visual model of the world had left out a key variable. Density is one of the ways physics quietly corrects us. Not with drama, just with a downward pull that says you may want to think again. It also helps explain why the densest ordinary materials are not necessarily the ones people expect. Heaviest atom does not automatically mean densest material. A very heavy element might not arrange itself as tightly as a slightly lighter one. Some elements are unstable, some are too rare, some do not form bulk matter in ways that matter for daily experience. What wins in practice is not sheer atomic heft alone, but the whole package. Mass, structure, stability, packing. The champion is the one whose atoms not only weigh a lot but know how to sit close together without ruining the arrangement. This is one reason osmium is such a satisfying answer. It sounds exotic, yet the reason for its density is not mystical. It is simply what happens when nature combines very heavy atoms with a crystal structure that waste very little space. Iridium nearly matches it for similar reasons. Tungsten follows close enough to remain the more practical star of demonstrations. Gold and platinum remain wonderfully dense examples that many people already know by reputation and by touch. Even so, there is a hard stop to how far this ordinary parade can go. No matter how dense these metals are, they do not come anywhere near the densities found in stellar remnants. Not because the elements are too weak or too lazy, but because ordinary atoms are still ordinary atoms. Their electrons maintain separation, their nuclei remain distinct. The material is dense, yes, but it still belongs to the everyday regime in which chemistry makes sense, and a chunk of matter can sit on a table without becoming the local gravitational authority. And that last point is easy to overlook. The densest ordinary matter on Earth may be heavy enough to impress your muscles, but it does not meaningfully alter the world around it through its own gravity. A gold bar does not attract your keys off the shelf. A tungsten block does not noticeably bend the floor toward itself. Its mass is large on the scale of a hand, but tiny on the scale required for gravity to become personally expressive. Earth still does almost all the work. That is what makes the next step so dramatic. Once you leave ordinary atomic matter behind, density increases not by small percentages or close rivalries at the top of a chemical table, but by leaps so enormous that the comparison almost becomes unfair. The densest metals on Earth are like the strongest people in a village. Very impressive, absolutely real, and nowhere near the scale of a mountain. Still, they matter, because they mark the end of common experience. They are the last stop before intuition becomes badly underqualified. If you want to know how much mass a hand-sized object can contain, without asking atoms to surrender their normal structure, this is your answer. Not lead, despite its cultural fame. Not some mystery stone from a fantasy story. The real champions are the heavy metals whose atoms carry great mass and crowd together efficiently. Osmium and iridium at the summit, tungsten not far behind and far easier to imagine as an actual object, with gold and platinum reminding us that density has often been admired for social reasons long before it was appreciated scientifically. And yet, for all their heft, every one of these materials is still playing by rules that stars can break. They are the densest matter we meet on Earth. but not the densest matter the universe can make. They are what ordinary atoms can do when nature pushes them close to the practical limit of chemistry, not what matter does when gravity itself becomes the great compressor and insists that atoms stop behaving like atoms at all. That is where the real escalation begins. Because once you ask what happens if you keep squeezing beyond the comfort zone of metals and crystals and electron clouds, the conversation leaves the periodic table behind and starts moving toward the point where familiar matter gives up its familiar structure. There is a quiet assumption built into almost all of daily life, and it is so familiar that we rarely bother to notice it. Matter keeps its shape well enough for us to trust it. Tables stay table-shaped. Cups remain cup-shaped. Stones do not slowly collapse into denser stones for lack of ambition. We live among materials that seem to have made a long-term agreement with their own structure. Wood remains wood. Steel remains steel. Even the densest metals on Earth, for all their impressive heft, still behave like respectable citizens of the ordinary world. They sit there, dense and solid and uncomplaining, without doing anything especially theatrical. But that calm behaviour depends on a hidden balance. Atoms are not just little lumps placed side by side like oranges in a crate. They are systems with rules. They have a nucleus at the centre, electrons arranged around it, and a set of quantum restrictions that determine how close one atom can comfortably approach another without everything becoming expensive in energy and highly unpleasant in consequence. Ordinary matter is stable not because it has reached the maximum possible compactness, but because it has reached a workable compromise. The atoms are close enough to form solids and liquids and everything else we know, but not so close that their internal structure has to be abandoned. That is why the next question matters so much. What happens when that compromise is broken? What happens when atoms are squeezed too far? At first, the answer still sounds familiar. If you compress a material a little, it resists. A sponge is easy to compress because its structure includes obvious empty space. A rubber ball resists more strongly. A steel rod resists far more strongly still. The more tightly bound and compact the material, the less willing it is to change shape under pressure. This is all part of ordinary mechanics. Materials deform. They spring back or they do not. They bend, crack, heat up, buckle, or shatter. Engineers worry about this sort of thing all the time, and it keeps bridges upright and beverage cans from becoming philosophical. But if we keep pushing, if we imagine pressure increasing far beyond anything a workshop press or hydraulic machine could hope to manage, then the response of matter stops being just a matter of strength. It becomes a matter of atomic identity. The atoms are no longer merely being nudged closer. Their electron structures are being forced into arrangements they do not like. The spacing between atoms shrinks. The electron clouds begin to overlap in more serious ways. The material does not simply become a tougher version of itself. It enters a regime where the very concept of ordinary solid matter starts to strain. This is the first important turn in the whole story. When atoms are squeezed too far, matter does not politely continue down the same path it was already on. It changes character. The pressure begins to compete not just with chemical bonds, but with the quantum rules that determine how electrons can occupy space and energy states. In ordinary matter, electrons are arranged according to strict rules that keep them from all piling into the same condition. You can think of this less as personal preference and more as a hard universal refusal. Electrons are not social in the way marbles are. They do not all sit happily in the same lower state if the universe offers them the option. They have to stack into different allowed states, which creates a kind of built-in resistance when matter is compressed. That resistance is subtle in everyday life, because so many other effects dominate first. A chair leg does not collapse because the electrons in its atoms have been forced into a crisis. It collapses because the material breaks at the scale of grain structure and chemical bonding. But under immense pressure, that deeper resistance becomes one of the main reasons matter can support itself at all. It is as though ordinary atomic structure hands over the responsibility to a more fundamental rule and says, "I have done what I can." This is exactly the sort of handover that happens inside stars when they run out of easier ways to support themselves. A star, during most of its life, is held up by an internal contest. Gravity pulls inward, always patient, always trying to compress the whole thing further. The hot interior pushes outward through pressure created by intense temperature and nuclear processes. For millions or billions of years, depending on the star, this contest can remain in a rough balance. But stars are not eternal. They consume fuel. Conditions change. And once the ordinary thermal support begins to fail, gravity gets a chance to press harder than matter would ever experience on the surface of a planet. This is where the phrase "squeeze too far" stops being a metaphor and becomes a literal description of stellar death. In the collapsing core of a star, atoms are driven closer and closer together under pressure so extreme that their ordinary arrangements can no longer survive. Electron shells, those regions that define so much of chemistry and ordinary material behavior, are no longer the governing story. The compression becomes so severe that electrons are stripped from their usual atomic relationships. Matter turns into something more like a densely packed sea of nuclei and electrons rather than a tidy assembly of recognizable atoms. That may not sound dramatic at first hearing, but it is an extraordinary shift. Chemistry lives in the behavior of atoms and their electrons. If atoms stop existing in the ordinary sense, chemistry stops being the appropriate language. You're no longer dealing with gold or carbon or iron as materials with familiar atomic personalities. You are dealing with matter in a more stripped down state. Matter under conditions so severe that the spaciousness of everyday atoms has been largely erased. There is something deeply strange about that because atoms are already so small that most of us treat them as the end of the road. We are taught that matter is made of atoms, and that sounds final enough for most purposes. But physics is never especially impressed by what sounds final to us. Atoms are just one level of organization. They can be rearranged, ionized, crushed, fused, or destroyed as ordinary atoms under the right conditions. The word atom originally suggested indivisibility. Nature, as usual, did not feel obliged to honor the branding. The first extreme state reached after ordinary atoms give up their familiar structure is associated with white dwarfs, though we will spend more time with those proper in the next stretch. For now, what matters is the transition itself. In a white dwarf, matter has been compressed so strongly that electrons are no longer attached to individual atoms in the normal way. The material is supported by a kind of electron pressure, rooted in quantum rules rather than by ordinary heat or standard chemical structure. It is no longer sensible to picture it as a pile of atoms sitting together like tiny balls in a box. It is more like atomic nuclei embedded in an electron background so compressed that the whole thing behaves in a way with no everyday equivalent. If you tried to explain this to someone using kitchen examples, you would run out of kitchen very quickly. A compressed gas still belongs to ordinary intuition. A compressed spring still belongs to ordinary intuition. Even a diamond, hard and dense and admirable, still belongs to ordinary intuition if you squint a little. But white dwarf matter does not. It is what happens when gravity becomes a pressure machine on a stellar scale. An ordinary atomic architecture is replaced by a more severe arrangement, and yet even that is not the end of compression. Suppose gravity presses harder still. Suppose the object is more massive or the collapse more violent. Then even the state supported by those crowded electrons can fail. The electrons themselves are forced into encounters with protons under such extreme conditions that they are no longer able to remain separate in the old way. They combine, and the matter is driven into another regime, one in which neutrons dominate. At that point, you are no longer just squeezing atoms until they lose their electron shells. You're squeezing matter until one of its very basic internal balances changes. The distinction between protons and electrons as separate large-scale populations becomes less useful. Neutron-rich matter takes over. That leap is so large that it almost makes the destruction of ordinary atoms look like a warm-up exercise. First chemistry disappears. Then even the familiar particle arrangement of nuclei and free electrons becomes unstable under sufficient pressure. This is one of the great lessons of astrophysics. Matter has levels of surrender. It gives up ordinary bonding before it gives up atomic identity. It gives up atomic identity before it gives up the separate existence of electrons and protons in bulk. Gravity keeps asking for more compactness, and matter keeps finding new ways to resist until those ways are exhausted. There is a wonderfully grim practicality to this. Matter is not trying to be exotic, it is simply responding to pressure according to the rules available. Under modest conditions, it resists with chemistry and structure. Under harsher conditions, it resists with quantum restrictions on electrons. Under even harsher conditions, it becomes neutron-rich and finds a different sort of support. And if gravity becomes strong enough that all of these responses fail, then the story heads toward black holes, where talking about matter as a substance with familiar properties becomes even more difficult. But let us not run that far ahead just yet, because there is still a great deal to appreciate in the moment when atoms first cease to be ordinary atoms. That threshold is one of the great dividing lines between the world we know and the more extreme universe beyond it. On one side are the materials of Earth, from water to tungsten, all governed by atomic and molecular structure in ways chemistry can describe. On the other side are stellar remnants, where matter has been stripped of that ordinary architecture and condensed into forms that owe more to gravity and quantum mechanics than to anything in a laboratory cupboard. If that sounds slightly intimidating, it helps to remember that the logic is simple even when the details are not. The densest ordinary matter on Earth is dense because heavy atoms are packed closely in normal structures. But those normal structures still contain plenty of room compared with what compression can achieve in a dying star. If gravity becomes strong enough, the electrons can no longer maintain the familiar spacing and arrangement that make atoms what they are. The matter is squeezed into something new. The object does not merely become a denser metal, it becomes a different class of matter. This shift also changes how we should imagine a hand-sized object. A hand-sized piece of tungsten would be heavy in a very understandable way. A hand-sized sample of matter that has been compressed beyond ordinary atomic structure would be heavy in a way that starts to become hard to think about sensibly. The amount of mass that could fit into that volume rises not by a little, but by orders so vast that intuition loses all authority. It would no longer be a curiosity for a science museum or a risky desk ornament. It would be a fragment of a stellar remnant, with consequences that reach far beyond sore fingers. There is also the question of stability, which becomes important here. Ordinary dense materials are stable under ordinary conditions. You can place gold on a table and trust it to remain gold on the table. But matter compressed into white dwarf or neutron star conditions is not something that naturally belongs on a table. Its existence depends on the environment in which it formed, on the surrounding pressure, and the gravitational circumstances that allow such a state to persist. Remove a tiny amount from that environment, and the result is not some neat portable sample in a display case. The physics becomes complicated very quickly. In practice, such matter would not simply sit there behaving itself for your inspection. This is worth emphasizing because the imagination likes to treat extreme matter as though it were just a more impressive version of a brick. But stellar matter is not a brick with better credentials. It is matter under conditions created by collapsed stars. Its structure is tied to an entire gravitational context. Thinking of it as something you could scoop into a bucket is a little like thinking of a tornado as a stronger form of house fan. The resemblance is not exactly wrong, but it is wrong enough to cause trouble. Still, as a thought experiment, it is useful to imagine what atoms squeezed too far really means. It means matter crossing a border. The borders of nature are often like this. At first, the behavior changes gradually. Then a threshold is crossed and the old description stops working. Water cools, then freezes. Iron heats, then glows. A star exhausts fuel, then collapses. Matter compresses, resists, rearranges, and finally ceases to be composed of atoms in the sense we usually mean. The transition may be driven by familiar gravity, but the result is not familiar at all. There is also something satisfying about how this answers the hidden question behind density. Why can the densest metals on Earth not simply be made denser and denser forever by brute force? Because at some point you are not making the same substance denser. You are changing what kind of matter it is. The electrons no longer permit the old structure. The atoms no longer survive as atoms. The process is not an extension of normal compression. It is a breakdown and replacement. And that replacement is not arbitrary. It follows from the deep rules of quantum mechanics and the balance between pressure and gravity. This is where the universe reveals one of its favourite habits. Under extreme conditions, the everyday description becomes not just incomplete, but misleading. The correct picture is usually stranger and often simpler in a severe kind of way. Ordinary matter is rich because atoms have room to be themselves. Extreme matter is sparse in possibility because pressure has taken much of that freedom away. By now, the path is becoming clearer. We began with dense, everyday materials and found the upper edge of ordinary atomic matter. Then we asked what happens when atoms are forced beyond that edge. The answer is that they do not remain politely atomic. Their electron structure breaks down under immense compression, and matter enters new regimes that only stars can normally create. The first of these is the regime associated with white dwarfs, where matter is crushed far beyond ordinary density, but not yet into the neutron-dominated state that comes later. It is the first real step into a universe where a hand-sized object could contain a quantity of mass so outrageous that all the dense metals of Earth would start to look almost airy by comparison, which is where the next part of the journey begins to feel properly unreasonable. To understand the strange weight of dead stars, it helps to begin with a very plain fact that rarely feels plain once you sit with it properly. Stars die badly. Not all in the same way, not all with the same violence, and not all on the same timetable, but none of them simply switch off like lamps. A star is not a flame in the everyday sense. It is not a thing that burns until the fuel runs out and then goes dark. It is a vast body of matter held in a long-running contest between gravity pulling inward and internal pressure pushing outward. For most of its life, that contest remains balanced well enough that the star appears steady, almost serene from a distance. It shines, it warms planets, it keeps its shape. But underneath that appearance is a constant struggle. Gravity is always waiting for the chance to compress the star further, and the star survives only because something inside keeps pushing back. That balance is the key to everything that follows. A living star, if we want to use that language for a moment, is supported by activity. Deep in its interior, nuclear processes release energy. That energy helps maintain pressure. The details differ depending on the mass of the star and its stage of life, but the broad picture remains the same. As long as the inside can keep resisting gravity, the star can remain a star. Once that resistance weakens or changes, the old arrangement cannot hold forever. Gravity gets the upper hand, the core contracts, conditions become more extreme, and from that collapse come some of the strangest objects in the universe, remnants that contain enormous mass in absurdly small volumes and make all ordinary ideas of heaviness feel provincial. This is why the dead star matters to our original question. If you want to know how heavy a small object can be, you eventually have to leave Earth and consult the ruins of stars. The densest materials we encounter here are still ordinary matter. They are made of atoms behaving in recognizable ways. Dead stars are what you get when gravity pushes matter past that recognizable limit. They are not just heavier versions of familiar objects. They are matter in a different condition. Matter forced into arrangements that only immense gravitational collapse can produce. The phrase dead star may sound slightly dramatic, but in astrophysics it points to something specific. A star spends most of its existence fusing lighter nuclei into heavier ones in its interior. That process provides energy, and the release of energy helps maintain the pressure needed to oppose gravity. Eventually, however, the star exhausts the combinations that are useful for support. It may swell and change and shed layers. It may flare or pulse or blow off its outer atmosphere. But the central issue remains. The inner support system changes, and the core is left in a state where gravity can compress it more effectively than before. What remains after that depends very strongly on the mass of the star. Some stars leave behind white dwarfs. More massive ones can collapse into neutron stars. The most massive cases, under the right conditions, continue toward black holes. What links all of these remnants is that they are compact. Gravitational collapse has taken a huge amount of matter and squeezed it into a much smaller object. The weight becomes strange not simply because the remnant is heavy, but because it remains heavy after becoming small. A living star can be enormously massive, of course, but its size is also enormous. Much of the shock of stellar remnants comes from the mismatch. A white dwarf can contain a mass comparable to that of a star while shrinking to a size much closer to that of a planet. A neutron star can compress even more dramatically, taking more mass than our Sun, and fitting it into a sphere that would look almost modest on a planetary map. The mass has not vanished. It has been concentrated, and that concentration changes everything. If you could stand at a safe conceptual distance and look at one of these remnants with the habits of everyday thought still intact, you might initially misunderstand what you were seeing. A white dwarf, from far away, might sound manageable compared with a giant star. A neutron star, if described only by its size, might sound almost toy-like on the cosmic scale. But size is the great trickster here. These objects are not small in the sense that a pebble is small. They are small for what they contain. Their strangeness comes from the amount of mass gravity as packed into that reduced space. That is also why the word dead can be misleading in a useful way. A dead star is not inactive in the ordinary sense. It is not a cold cinder in a fireplace, something that once did interesting work and now merely occupies room. A stellar remnant is often more physically extreme than the star that produced it. It may no longer shine through the same processes, but it carries the consequences of collapse. Its gravity is fierce. Its matter is compressed beyond anything chemistry can describe properly. Its surface conditions can be extraordinary. In some cases it spins rapidly. In others it carries intense magnetic fields. It is not lifeless in any simple physical sense. It is the aftermath of a failure of one balance and the creation of another, harsher balance. White dwarfs are the gentler of the two main dead star remnants we're considering first, though gentle is doing some heavy lifting in that sentence. They form from stars that are not massive enough to collapse all the way to the next level. When the star sheds its outer layers and the core is left behind, gravity compresses that core until a new kind of pressure takes over, one rooted not in the ordinary heat of the living star, but in the quantum rules governing electrons. The result is a compact object with a great deal of mass packed into a volume much smaller than before. It is no longer powered in the old way. It is no longer a fusion-driven star in the usual sense, but it is astonishingly dense. Neutron stars go further. They form when a more massive star undergoes a more violent collapse. The pressure becomes so intense that matter is driven past the white dwarf state. Electrons and protons are forced into a new arrangement, and neutron-rich matter dominates. What remains is even smaller and vastly denser. If white dwarfs are already a challenge to intuition, neutron stars are a deliberate insult to it. They take the logic of compression and push it into a regime where the numbers stop being vivid and start being almost confrontational. There is an important emotional fact hidden in all this, and it is one of the reasons people find stellar remnants so gripping, even if they do not think of themselves as astronomy people. The universe usually allows us to ignore density. Most things around us occupy the range of densities that bodies and brains evolve to navigate. We know how wood behaves, how stone behaves, how metal behaves, roughly speaking. But dead stars expose the far end of the scale. They reveal that matter can be packed so tightly that our everyday categories are not merely incomplete, but almost silly. A hand-sized amount of white dwarf matter or neutron star matter is not just heavy, It is heavy in a way that makes ordinary comparisons struggle to survive. Still, before we get to the thought experiment of a handful, which comes next, it helps to appreciate the dead star on its own terms. What does it mean for an object to have strange weight? It means that the relationship between size and mass is no longer intuitive. It means gravity has done enough work that the remnant carries a kind of physical seriousness out of all proportion to its dimensions. It means that the object is no longer just something the planet would pull downward. It is something whose own gravity begins to matter much more strongly than that of ordinary objects. A white dwarf or neutron star is not only hard to imagine holding, it is hard to imagine being near without the rest of the environment having firm objections. That gravity has visible consequences at the scale of the whole object. White dwarfs are compact enough that their surface gravity is far stronger than anything we know in daily life. Neutron stars are far more extreme still. The pull near their surfaces is so intense that matter behaves differently simply because of where it is. You could not stroll across such a surface in any meaningful sense. The very notion belongs to the category of cheerful misunderstandings. The environment around these remnants is already shaped by the density they contain. Their strange weight is not a private property locked inside them. It expresses itself outwardly through the strength of their gravity. This begins to answer another quiet question that may have been forming in the background. Why should we care about density rather than mass alone? Because mass alone does not tell us how dramatically an object influences its surroundings. Spread enough mass over a large enough volume, and the result can be relatively mild locally, even if the total is huge. Compress that mass into a much smaller region, and suddenly everything changes. The gravitational field near the object strengthens. The energy associated with falling toward it increases. The object starts to act less like a large familiar thing and more like a compact authority in its own right. Dead stars are strange because they reveal what gravity can do when mass is concentrated rather than spread out. There is also something satisfying about how they form. The living star spends most of its existence resisting collapse with energy generated in its interior. But when that era ends, the remnant that remains is supported differently. In a white dwarf, the support comes from electron-related quantum pressure. In a neutron star, the support comes from the behavior of matter compressed into a neutron-rich state, and the deeper forces operating there. In both cases, the dead star is not held up by the same process that supported the living one. It has become a new kind of object with a new way of opposing further collapse. That is part of what makes it feel alien. The star has not just shrunk, it has changed category. And category changes are where physics becomes most interesting. Water boiling is interesting because a liquid becomes a gas. Iron magnetizing is interesting because many tiny internal alignments suddenly matter together. A star collapsing into a white dwarf or neutron star is interesting because matter gives up one mode of existence and adopts another under immense pressure. The strange weight of dead stars is really the weight of matter after it has crossed one of the great borders in nature. One way to keep this grounded is to think about what has happened to the empty room inside matter. Ordinary atoms contain vast internal spacing compared with the size of their nuclei. That does not make ordinary matter insubstantial, because the rules governing electrons make it perfectly solid to us. But it does mean there is a great deal of structural room in atomic matter, room that gravity can eliminate under the right conditions. In a white dwarf, much of that spaciousness has been squeezed away. In a neutron star, the compression is more severe still. The strange weight of dead stars is, in a sense, the weight of room removed. That phrase may sound neat, but it points to a brutal physical truth. The dead star is what remains when gravity has stripped matter of much of the freedom it enjoyed before. Atoms are no longer allowed their usual comfortable spacing. Electrons are no longer behaving as they do in ordinary matter. Later, even that arrangement fails and neutron-rich matter emerges. With each stage, the same amount of matter occupies less space, and with each stage, the weight of a small sample grows more outrageous. It is worth pausing here to notice that the universe does not create these objects casually. The pressures involved are not remotely available on the surface of the Earth. You do not get a white dwarf by squeezing a metal block in a very determined workshop. You do not get a neutron star by stacking enough lead weights in the garage and trusting enthusiasm to do the rest. These are products of stellar evolution and collapse, forged by gravity operating on scales so large that the resulting matter states are effectively impossible in any ordinary terrestrial setting. That is why they retain a certain dignity even in thought experiments. They are not curiosities. They are endpoints of stars, and yet they are also remarkably concrete. This is not speculative fantasy. White dwarfs exist. Neutron stars exist. We detect them, study them, model them, observe their effects on companions and surroundings. Some announce themselves through pulses. Some reveal themselves in binary systems. Some are inferred through the radiation emitted as matter falls toward them. Dead stars are not symbolic. They are out there, carrying their strange weight with complete indifference to our difficulty picturing it. If anything, the hardest part is not believing in them but emotionally adjusting to what their density implies. We are comfortable thinking in scales where a mountain is heavy because it is large, and a coin is light because it is small. Stellar remnants scramble that comfort. They ask you to accept that a star can lose its ordinary life and leave behind something not large by stellar standards, and yet still packed with an enormous fraction of stellar mass. The object becomes a concentrated reminder that matter has far more possible arrangements than our bodies ever needed to know. There is also an almost unfair elegance to the sequence. First, the ordinary star balances gravity through internal energy. Then, when that support cannot continue, the remnant balances gravity in a more severe way. White dwarf if the mass is low enough, neutron star if it is higher, black hole if even neutron star matter cannot hold the line. It is one of the clearest ladders in astrophysics, a progression through increasing compression and increasing density, with each rung revealing a deeper level of how matter resists being crushed. The strange weight of dead stars sits right in the middle of that ladder, where the story stops being about familiar materials and starts being about the limits of matter itself. What makes white dwarfs especially useful at this stage is that they are the first stop beyond ordinary atoms. They are already extreme enough to feel impossible, yet they remain just shy of the even more dramatic neutron star regime. They are the place where our original question begins to become quantitatively absurd without yet becoming completely savage. A hand-sized amount of white dwarf matter would already be so heavy that the phrase hand-sized begins to sound like trap, and that makes white dwarfs a perfect next step. They are not the end of density, but they are the first dead stars whose strange weight we can use to bridge the gap between dense metals and truly catastrophic compactness. So the dead star in this part of the journey is not just an astronomical detour, it is the answer to a structural problem in nature. How far can matter be compressed once ordinary atoms have been squeezed too far? Far enough to create remnants with mass, concentrated to a degree no earthly material can approach. Far enough that size becomes a poor guide, and gravity becomes a much more vocal participant. Far enough that a tiny imagined sample starts to outweigh all the respectable objects of ordinary experience by such a margin that comparison begins to turn into comedy. That is why the next question is the natural one. Not yet the neutron star, not yet the black hole, but the first of the dead stars that teaches us what truly compressed matter feels like in principle. If a white dwarf is the gentler ruin of a star, if it represents matter beyond ordinary atomic structure, but before the full severity of neutron star collapse, then what would a hand-sized amount of that matter actually mean? Not in an equation, not as a vague statement that it would be heavy, but in concrete physical terms. How much mass would that small volume contain? What would it do to the world around it? And why does a dead star that looks modest by cosmic standards already make the idea of holding something in your hand start to sound less like a thought experiment and more like a very direct threat to the floor? A handful of white dwarf matter is the point where our original question stops being mischievous and starts becoming almost unfair. Up to now, we have been able to talk about dense metals with a straight face. We could imagine tungsten on a desk, gold in a vault, iridium in a laboratory, all heavy in a way that still belongs to the ordinary world. Even when those materials feel surprisingly weighty for their size, they remain understandable. They are atoms arranged in familiar ways. Their density is impressive, but it still belongs to chemistry. White dwarf matter is the first place where chemistry no longer gets to feel in charge. A white dwarf is the leftover core of a star like the Sun, after it has exhausted its nuclear fuel and shed much of its outer material. What remains is typically about half the mass of the Sun, packed into a body only slightly bigger than Earth, which is why white dwarfs rank among the densest forms of matter in the universe, surpassed mainly by neutron stars and black holes. That combination alone should already feel a little indecent. Half the mass of the Sun sounds like the beginning of one story. Slightly bigger than Earth sounds like the beginning of another. The fact that both statements refer to the same object is what gives a white dwarf its strange weight. NASA describes white dwarfs as roughly 1,000,000 times denser than matter on Earth, and uses wonderfully plain comparisons to make that less abstract. One NASA page says a teaspoon of white dwarf material would weigh more than a pickup truck. Another says a tablespoon from the surface would weigh as much as a school bus. These are not decorative metaphors. They are attempts to translate a stellar fact into a human scale. And even then they only partly succeed, because the mind keeps trying to file the object under spoonful, and the physics keeps insisting on vehicle. So let us try the thought experiment carefully. Imagine a quantity of matter no bigger than what you might cradle in one hand. Not a whole white dwarf, of course, because that would be absurd on several levels at once, but a hand-sized sample of the stuff that makes up a white dwarf interior. Immediately the phrase hand-size begins to lose its innocence. It still tells you the volume, but it tells you almost nothing about the mass. If a teaspoon can outweigh a pickup truck and a tablespoon can rival a school bus, then a whole handful rises so quickly beyond ordinary comparison that the hand itself starts to seem like the wrong tool for thinking about it. The point is not that your hand would merely struggle. The point is that this is no longer a lifting problem. It is a density problem so extreme that lifting becomes the least interesting part of the disaster. What makes white dwarf matter so different is not that it contains some magical new ingredient. It is still made from the same basic constituents as ordinary matter. The difference is what gravity has done to the arrangement. In a normal solid on Earth, atoms retain their familiar structure. Nuclei sit at the centre, electrons occupy allowed states around them, and the spacing between atoms is large compared with the size of the nuclei themselves. In a white dwarf, the collapse of the stellar core has squeezed matter so tightly that atoms in the ordinary sense no longer survive as roomy little systems with their own private electron territories. The material becomes electron degenerate. The object is held up not by ordinary thermal pressure, and not by chemistry, but by quantum mechanical forces associated with electrons packed into extremely cramped conditions. That is why a white dwarf can remain stable as a compact object instead of simply continuing to collapse at once. There is something deeply useful in noticing that phrase, held up. It reminds us that a white dwarf is not merely dense because it happens to have settled that way. It is dense because gravity has spent an entire stellar lifetime waiting for its chance. And once the old support of the star weakens, gravity compresses the core until a new form of resistance takes over. In an ordinary star, pressure from heat and fusion helps resist collapse. In a white dwarf, the star is no longer generating energy in that old way. NASA notes that white dwarfs produce no new heat of their own, and instead cool gradually over billions of years. What keeps them from collapsing further, at least below a certain mass threshold, is electron degeneracy pressure. The result is a compact remnant that is no longer an active star in the main sequence sense, yet is far more extreme in density than the star ever was while living its calmer, more spacious life. This helps answer an important hidden question. Why can a white dwarf be so dense without instantly becoming something even more dramatic? because nature has found another way for matter to push back. The electrons, crowded by collapse, resist being packed into the same states. That resistance is not the kind you feel when squeezing a spring or compressing a pillow. It is a quantum rule asserting itself on a stellar scale. ESA notes that once a white dwarf exceeds about 1.44 times the mass of the Sun, this electron-based support is no longer enough. Then the pressure becomes so great that electrons are forced into nuclei, pushing the object toward the next stage, where protons and electrons combine and neutron-rich matter takes over. In other words, a white dwarf is not the final word in density. It is the first truly extreme pause point after ordinary atoms have given up their usual structure. Now, if we stubbornly continue with the imagined handful, the next thing to notice is that heaviness would stop being a local inconvenience and start becoming an environmental event. A block of tungsten on a table is heavy because Earth pulls it downward. A handful of white dwarf matter would certainly still be in Earth's gravity, but it would also carry far more mass in that tiny volume than any ordinary object ever could. White dwarfs as whole stars already have surface gravity that ESA says can exceed 100,000 times the gravity at Earth's surface. That figure refers to the star itself, not to a hypothetical sample sitting in your palm, but it tells you what sort of object you're borrowing from in this thought experiment. The material comes from a place where gravity and density are already in a far more intimate relationship than anything in everyday life. And this is where the humour, if there is any left, becomes very dry indeed. We began with the idea of fitting something in your hand. With white dwarf matter, the phrase still fits in your hand is technically about size, but not about practicality. You do not wonder whether your fingers are strong enough in the way you might wonder about a dumbbell or a dense stone. You wonder what the floor would think of the arrangement. You wonder what the surrounding structure would think. You wonder whether nearby matter, including your own body, would appreciate being so close to such concentrated mass. Even without chasing exact force calculations, the central fact is enough. This would not be a paperweight. It would be a compact insult to ordinary engineering. The room would become part of the story very quickly. There is another complication, and it is an important one if we want the thought experiment to stay honest. A literal portable chunk of white dwarf matter is not something astrophysicists expect you could simply remove from a white dwarf and place on Earth as though it were a souvenir. White dwarf matter exists as part of a compact star supported by immense gravity and electron degeneracy. The whole object is in equilibrium under those conditions. So when we talk about a handful, we're using a conceptual sample to understand density, not describing a realistic procurement plan involving a container, a shovel, and deeply regrettable confidence. That is an inference from how white dwarfs are structured and supported, and it matters because the point is not that you could own such a sample. The point is that this is what matter can become when a star has collapsed far beyond the normal atomic world. Still, even as a conceptual sample, the exercise is incredibly revealing. It tells us how much of ordinary matter is really arrangement rather than irreducible compactness. The densest metals on Earth feel substantial because their atoms are heavy and packed efficiently, but they still preserve atomic spacing and recognizable structure. A white dwarf does not. Much of that familiar spacing has been crushed away. The result is matter that is not just denser by a tidy factor, but denser by an amount large enough to make earthly materials seem almost fluffy by comparison. NASA describes white dwarfs as about 1 million times denser than matter on Earth, while Britannica likewise describes average densities approaching about 1 million times that of water. Once you hear those comparisons enough times, everyday solids begin to look less like the final form of matter and more like its relaxed setting. There is also a subtle shift in how we should imagine the object. A dense metal block is still a block in the ordinary tactile sense. It has a surface you could tap, a temperature you could feel, and a mechanical behaviour that engineering tables know how to discuss. White dwarf matter belongs to a very different category. NASA notes that most white dwarf atmospheres contain a single atom, often hydrogen, while the broad spectral lines seen from white dwarfs are related to the intense pressure at their surfaces. That pressure is already a clue that this is not simply matter with extra weight added. It is matter existing under conditions that alter atomic behavior at the surface and destroy ordinary atomic comfort in the interior. So when you imagine a hand-sized piece, you should not picture a more elite version of a metal ingot. You should picture a sliver of a stellar remnant with all the severe physics that phrase implies, and yet for all its extremity, white dwarf matter is still the mild member of the dead star family. That is one of the strangest parts. A white dwarf already feels almost impossible from the standpoint of daily experience. Its mass is star-like, its size is roughly planetary, its density humiliates every material on Earth, its support comes from quantum rules asserting themselves against gravity, and still, in the larger sequence of collapsed objects, this is not the harshest version. This is the compromised state before collapse goes further. If the remnant is too massive, the electron support fails, and the matter is pushed onward into the neutron star regime. So a handful of white dwarf matter is not the end of the story about compactness. It is the first place where the story becomes openly unreasonable, while still preserving a kind of intermediate dignity. That is why it is such a useful stepping stone in our question. It allows us to feel the scale break. Up to this point, we could still pretend that dense meant something like impressively heavy. White dwarf matter forces a correction. Dense can mean so much mass in so little space that ordinary material language becomes inadequate. Heavy no longer means hard to carry. It means belonging to a regime of collapsed stellar remnants. It means that a spoonful can be compared with a truck, not because someone is being colourful, but because that is genuinely the sort of weight involved. Once that door is open, our original question changes its tone. We're no longer asking for the strongest everyday material. We're asking how far the universe allows matter to be compressed before matter itself changes category again. There is a nice irony in this. White dwarfs are often described as the fate of stars like the Sun, which makes them sound almost domestic by stellar standards, the quiet retirement plan of moderate stars. And in one sense that is true. They are the endpoint for many ordinary stars in the galaxy. But their ordinary origin hides an extraordinary result. A star can live an unremarkably stable life for billions of years and still end as an object whose matter is compressed beyond ordinary atoms, whose density dwarfs everything on Earth, and whose imagined handful becomes a lesson in why scale is such a treacherous guide to reality. The universe is very good at producing this kind of mismatch. The outcome sounds modest until you inspect it. Then suddenly a dead stellar core becomes one of the densest states of matter, short of even more alarming company. So if someone asked, quite innocently, what is the heaviest thing that could still fit in your hand, white dwarf matter, is where you first have to stop smiling politely and say that we need to redefine what sort of answer they are prepared to live with. Because yes, a hand-sized amount could exist in imagination. Yes, its size would still be hand-sized, but its mass would belong to the world of stellar remnants, not the world of human objects. It would not be something you hold so much as something whose existence nearby would make holding seem like the least interesting verb available. And even that is not yet the truly vicious answer, because if white dwarf matter represents atoms squeezed past their ordinary limits, but still supported by electron degeneracy, then the next step is matter driven further still, past the point where even the electrons can no longer hold the line, into the regime where a hand-sized amount stops resembling a ruin of ordinary matter and starts resembling the interior logic of a neutron star. If white dwarf matter is where atoms lose their ordinary structure, neutron star matter is where even that intermediate arrangement gives way to something harsher. This is the next step after gravity has already won a great deal of ground. A white dwarf is held up by the resistance of electrons crowded into extremely tight conditions. A neutron star forms when the collapsing core of a more massive star pushes beyond even that limit. The pressure rises so far that electrons and protons are no longer able to remain comfortably separate in bulk. They are driven together, and the result is matter dominated by neutrons. At that point, the question is no longer how tightly atoms can be packed. Atoms, as such, are finished. Even the white dwarf version of matter is finished. You're now in a regime where the familiar architecture of matter has been stripped down to something far more severe. This is one of the sharpest transitions in all of astrophysics because it marks a point where ordinary intuition is not just stretched but actively defeated. We can still talk sensibly about dense metals. We can even talk with some effort about white dwarf matter as a star remnant in which ordinary atomic spacing has been crushed away. But neutron star matter takes another large step outward from common experience. It is what matter becomes when gravity compresses it so strongly that a stellar core collapses into an object only a few tens of kilometers across, while retaining more mass than the Sun. That sentence is already enough to unsettle the mind a little. More mass than the Sun sounds like a large object. A body only a few tens of kilometers across sounds, on a cosmic scale, almost modest. Both descriptions belong to the same thing. What makes neutron star matter so remarkable is not only the density itself, but the way that density is achieved. In ordinary matter, electrons occupy their own allowed states around nuclei, and atoms maintain a recognizable identity. In a white dwarf, the atoms have already been pushed beyond that recognizable form, but the material is still supported by the crowded resistance of electrons. In a neutron star, that support is no longer enough. The pressure becomes so intense that electrons are forced into combination with protons. The old separation between positively charged nuclei and surrounding electrons gives way. Neutrons become the main inhabitants of the matter, and the star settles into a new equilibrium, supported by neutron-rich matter and the deeper forces that act within it. That phrase, deeper forces, matters more than it may first appear to. In everyday life, matter behaves mostly through electromagnetism, chemistry, and ordinary mechanics. A chair supports your weight because of the electromagnetic interactions and structures inside its material. A metal bar bends or resists bending because of the same broad category of interactions. Even a white dwarf, extreme as it is, still involves the role of electrons pushing back in a quantum mechanical way. But neutron star matter belongs more directly to the domain where the strong nuclear force becomes central to how matter resists collapse. This is not the force that usually dominates your morning routine. It is not why your spoon stays spoon-shaped. It is one of the fundamental interactions of nature, and in neutron stars it becomes part of the main supporting machinery. That alone should make clear why neutron star matter is not just a more concentrated version of ordinary material. It is matter under conditions so extreme that the very rules most relevant to its large-scale behavior are not the ones we rely on in daily life. It would be misleading to picture neutron star matter as some especially firm kind of metal or some fantastically compressed rock. Those analogies fail almost immediately. Neutron star matter is not like a tougher version of earthly stuff. It is a new state, born out of collapse, maintained by forces that only become decisive under extraordinary density. Even so, there is value in moving slowly here, because the phrase matter dominated by neutrons can sound simpler than it is. It is tempting to imagine the neutron star as one enormous atomic nucleus, just a big ball of neutrons with no further subtlety. That picture contains a grain of truth, but leaves out a great deal. Neutron stars are thought to have layers. Their outer regions may still include a crust of nuclei and electrons arranged in increasingly strange patterns as depth increases. Beneath that, the matter becomes more and more neutron-rich. Farther in, conditions become so extreme that physicists are still working out exactly what the material is doing. There may be superfluid behavior, there may be exotic particle populations, there may even be forms of matter involving more fundamental constituents in ways not yet fully settled. Neutron star interiors are one of those places where theory is powerful, observations are improving, and uncertainty remains not because the subject is vague, but because nature has made the laboratory very far away and rather difficult to open. That uncertainty is important because it shows the honesty of the science. We know neutron stars exist. We know a great deal about their masses, sizes, magnetic fields, rotation, and the broad picture of how they form. We know that their matter is compressed beyond ordinary atoms and beyond the white dwarf state. But when you ask exactly what the deepest interior looks like, physics becomes more exploratory. Different models make different suggestions about what particles may appear and how the matter behaves at the highest densities. There is nothing embarrassing about that. It is what the frontier looks like. The broad structure is secure, the fine details are still being interrogated, and yet even without settling every interior detail, the central lesson for our question is already clear. Neutron star matter is beyond atoms in a far more final sense than white dwarf matter. It is matter after gravity has forced a second surrender. First, the roomy structure of atoms is lost. Then, even the separate bulk existence of electrons and protons is driven into a new arrangement. What remains is so dense that a tiny quantity carries an amount of mass that makes white dwarf comparisons start to look almost moderate. This is where the imagination often reaches for simple comparisons and then regrets them. A neutron star is often described as a city-sized object with more mass than the Sun. That is useful as a first orientation, but only as a first one. The problem is that cities are familiar, and familiarity makes us underestimate the physical seriousness of the statement. A city is something with streets and buses and small arguments about parking. A neutron star may be similar in size to a city only in the loosest geometric sense. Physically, it belongs to a much harsher category. Its surface gravity is immense, its density is extraordinary, its magnetic field can be enormous, its rotation can be rapid enough that some neutron stars sweep beams across space like lighthouses, producing the pulsed signals that first revealed this class of object to astronomy in such a memorable way. That discovery itself is worth a brief pause because it illustrates how neutron stars entered human awareness, not as obvious objects to the eye, but through the effects of their compactness and rotation. Pulsars, which are rotating neutron stars emitting beams of radiation, were first noticed as highly regular pulses, so regular that the pattern at first struck some observers as almost artificial. The reality turned out to be much better than an artificial signal. It was nature revealing a dead star remnant so compact and so rapidly spinning that its emission appeared as precise cosmic beats. This is one of the pleasures of neutron stars. They are not only dense, they are physically expressive. Their compactness shapes their gravity, their spin, their fields, and the signals we can detect from far away. Still, the heart of the matter for us remains density. If neutron star matter is dominated by neutrons, why does that make it so much denser than white dwarf matter? The answer is that the compression has gone further inward. In a white dwarf, matter is already far beyond ordinary atomic form, but nuclei still remain as distinct ingredients in an electron sea. In a neutron star, much of that structure has been driven past the point of stability. The distinction between nuclei and electrons as large-scale organizing principles is no longer the main story. The material can be packed more tightly, because the previous arrangement has been abandoned. Gravity has forced matter into a state with far less internal room than even a white dwarf permits. There is something almost mercilessly logical about this. Every step of compression strips away a former luxury. Ordinary matter enjoys atoms. White dwarf matter loses those. White dwarfs still enjoy a form of support based on electrons as a crowded population. Neutron stars lose that too. If collapse continues still farther, even neutron matter cannot hold the line indefinitely, and black holes enter the story. Nature proceeds by taking away options. Matter resists using the rules available at a given stage, and when those rules are no longer sufficient, a more extreme stage appears. This makes neutron star matter a kind of central exhibit in the universe's lesson about density. It is not yet the total gravitational triumph of a black hole, where matter as an ordinary descriptive category becomes deeply problematic, but it is far beyond any state that chemistry or terrestrial engineering can approach. It sits in that dramatic middle region where matter still exists as matter in some meaningful sense, yet only under conditions so severe that our language starts relying on phrases like degenerate, superfluid, crust, core, and exotic phases. Neutron stars are what happen when the universe still permits an object to remain an object, but only just. One of the more intriguing possibilities in the outer and intermediate layers of neutron stars is the formation of structures sometimes referred to as nuclear pasta. The name sounds unserious, but the physics behind it is not. Under the intense pressure and density in certain layers, matter may organize into shapes that resemble sheets, tubes, or tangled patterns rather than neat isolated nuclei. These names are informal and memorable because the actual arrangement is so strange that ordinary geometric metaphors become useful. It is a good reminder that when matter is pushed into extreme regimes, it does not simply become featureless. It can develop new forms of structure governed by the contest between nuclear attraction and electric repulsion under crushing conditions. Even dead star matter, then, has texture in a conceptual sense. Not texture you would run a finger over, which would be an extremely short-lived experiment, but texture in how it organizes itself internally. Another striking feature of neutron star matter is that it may behave as a superfluid in the interior. In simple terms, that means parts of the matter can flow with extremely low internal friction under the right conditions. Superfluidity is already a strange concept in laboratory settings. Inside a neutron star, it becomes part of the large-scale behavior of a dead stellar core. This can even help explain certain observed features, such as sudden jumps in rotation known as glitches. The neutron star is so compact, so dense, and so physically exotic that its internal state can influence the timing of pulses observed across space. A star remnant can reveal its hidden interior not by letting us sample it, but by briefly changing the rhythm of its spin. The more one learns about neutron stars, the more unfair our original hand-size question begins to seem. We started with an object that could fit in your hand and asked how heavy it might be. The answer is turning out not to be a simple list of materials, but a tour through the death states of stars. Neutron star matter is the moment when the tour becomes openly violent. This is no longer a question of a dense object being hard to lift. It is a question of what matter becomes after the second great surrender to gravity. If a handful of white dwarf matter already strains the mind, a handful of neutron star matter practically announces that we're using the wrong verbs. Hold is no longer the point. The point is concentrated mass to a degree that would profoundly alter its surroundings. Yet it is exactly because neutron star matter is so extreme that it teaches us something valuable. It reveals that the limits of matter are not where daily intuition places them. Most of us grow up with a tacit scale of materials in our heads. Wood is light, stone is heavier, metals are heavier still, lead is very heavy. Then perhaps, if we are a certain kind of person, we discover tungsten and feel clever for a while. Neutron stars destroy that entire ladder. They do not merely add a rung at the top, they replace the building. They show that ordinary materials differ from one another within a narrow neighbourhood compared with what gravity can do on stellar remnants. There is also a conceptual pleasure in the fact that neutron star matter is still not necessarily the final word in the interior. Some models suggest that at the deepest densities, neutrons themselves may cease to be the last meaningful large-scale units, with quark matter or other exotic states potentially appearing. Whether that is realized in nature and under what conditions remains an active question. But even the possibility tells you something about where we are. Neutron star matter is not just beyond atoms. It may be near the threshold where even neutron-centered descriptions begin to strain. That is how far from ordinary material life we have traveled. And yet the path here was completely sensible. We did not teleport into abstraction. We began by noticing that small things can be surprisingly heavy. Then we asked what the densest ordinary matter on Earth is. Then we asked what happens when atoms are squeezed too far. Then the dead stars arrived. first in the form of white dwarfs, then in the harsher form of neutron stars. Each step followed naturally from the one before it. That is one of the best things about physics when it's working properly. The conclusions become extraordinary, without the reasoning ever needing to become theatrical. There is another reason neutron stars matter in this story. They are close to the point where the distinction between matter and gravity begins to blur in the practical imagination. A neutron star is still matter. It still has a surface. It still occupies space as an object. But its gravity is so strong and its compactness so severe that when you think about a small sample, the sample is not merely a piece of material. It is a concentration of mass with immediate gravitational consequences. The object cannot be separated in thought from what its gravity would do nearby. In that sense, neutron star matter prepares the mind for the final step toward black holes, where gravity ceases to be a companion to the object and becomes the dominant character in the entire discussion. Before we go there, though, there is an unavoidable practical question hanging in the air. It is one thing to say, neutron star matter is beyond atoms and astonishingly dense. It is another to ask what a hand-sized amount would actually do if it somehow appeared near you. Not simply how much it would weigh, but what it would do to the floor, the room, the air, the earth, and anything unwise enough to be nearby. Because with neutron star matter, the word heavy is no longer enough. The object is not merely difficult to carry. It is a compact catastrophe in waiting, and that is before we even reach the final limit where enough mass in a small enough space stops being a star remnant and becomes something from which not even light can escape. By the time we reach neutron star matter, the original question has changed its personality completely. At the start, asking what is the heaviest object that could still fit in your hand had a certain innocent charm. It sounded like the kind of thing you might wonder while holding a dense metal sample in a museum shop, or lifting some suspiciously weighty little object off a shelf, and thinking that seems unreasonable. But a hand-sized amount of neutron star matter is not unreasonable in the way a tungsten cube is unreasonable. It is unreasonable in the way a collapsing bridge is unreasonable. At that point, the issue is no longer whether your hand can lift it. The issue is whether the surrounding world could tolerate its existence for even a moment. And there is a second difficulty here that makes the thought experiment more honest if we face it directly. A hand-sized sample of neutron star matter is not something that could simply be cut out, boxed up, and brought home like a rather extreme geological specimen. Neutron star matter exists inside a neutron star because the whole object provides the pressure and gravity needed for that state to remain what it is. Remove a chunk from that environment, and you do not have an ordinary object in the sense we usually mean. You have matter whose stability depends on conditions that no longer exist around it. So before we even ask what it would do, we have to decide which fantasy we are allowing. Are we imagining that the sample somehow remains intact in its neutron star state despite being removed from the star, held together by some miraculous means that the universe has not actually agreed to provide? Or are we imagining what would really happen if such matter were somehow isolated and exposed to ordinary surroundings? Both versions are interesting. One tells us what a compact piece of neutron star matter would do if it remained neutron star matter. The other tells us why nature is not likely to let you run that experiment in the first place. Let us begin with the cleaner and more terrifying version. Suppose somehow that a hand-sized lump of neutron star matter could remain exactly as neutron star matter while sitting in front of you, not expanding, not evaporating into a more normal state, not instantly losing its compactness, just there, about the size of something you could cup in both hands if you were making very poor decisions. The first thing to understand is that its mass would be enormous beyond normal comparison. Even a tiny amount of neutron star matter contains far more mass than anything we ever meet in the everyday world. People often hear that a teaspoon of neutron star material would weigh around 1 billion tons, and assume that must be one of those educational exaggerations science communicators use when they worry the audience is not paying attention. It is not. It is simply the kind of scale involved when matter has been compressed that far. Now scale that up from a teaspoon to something hand-sized. Not a whole bowling ball, not a large bucket, just a compact object that would fit within the space your palm and fingers could roughly close around. The mass would rise so fast that all ordinary examples would stop helping. You would not be comparing it with trucks or buses or even ships for long. You would be talking about a concentrated amount of mass more at home in discussions of mountains, asteroids and industrial civilization than in discussions of things one person might hold. A hand-sized amount of neutron star matter could carry many tens of billions of tons of mass, depending on exactly how generously one defines a hand-sized volume. At that point, the language of lifting is already finished. No wrist, however optimistic, is entering the conversation. But sheer weight, in the ordinary downward sense, is only the beginning. A compact object that massive would not merely sit there waiting for Earth to pull on it. Its own gravity would become a very active participant. This is the point at which the thought experiment becomes less about an object and more about a local gravitational event. The lump would pull on the floor beneath it, on the air around it, on nearby furniture, on the building, on you. It would no longer be correct to think of it as just a very heavy thing. It would be a tiny but intense source of gravity in its own right. This is where the pleasant simplicity of our opening question breaks apart. A hand-sized neutron star object would not just be impossible to hold, it would begin affecting anything nearby in ways that no ordinary material ever does. And because it is so small, those gravitational effects would change very sharply with distance. One part of your body would be pulled more strongly than another part just a little farther away. That difference in gravitational pull across a short distance is what physicists call a tidal effect, and it is the sort of thing that turns calm astronomical descriptions into deeply personal bad news. Large ordinary objects do not produce noticeable tidal forces on the human scale. A hand-sized neutron star remnant would. If you brought your hand close to such a thing, the side nearest the object would feel a stronger pull than the side farther away. Not a poetic, stronger pull, a literal one. Fingers closer than the palm would be pulled harder. Skin closer than bone would not have the same experience. The shape of your hand would stop being mechanically irrelevant. Matter near the object would begin to feel gravity as a gradient rather than a simple downward tug. This is the same general principle that, on much larger scales, makes black holes so notorious in discussions of stretching objects into trouble. A neutron star lump would not be a black hole, but its compactness would make its nearby gravity change enough over short distances to become destructive. And then there is the flaw. A hand-sized neutron star object placed on Earth would not behave like a dense paperweight politely resting where you put it. If it somehow remained intact, it would be under the influence of Earth's gravity, while also carrying its own tremendous inertia and its own strong local gravitational field. The floor beneath it would not offer meaningful resistance for long. Whether concrete, steel, wood, tile, or polished museum stone, the material under it would be forced to participate in an experiment it never consented to. The object would punch downward, not because it is sharp or fast in the ordinary sense, but because so much mass concentrated into such a small volume would exert extraordinary pressure on the contact area. It is tempting to picture it simply falling through the floor like a lead ball through wet cake, but the real situation is less tidy and more catastrophic. The local stress would destroy the structure beneath it almost immediately. The object would plunge downward into the Earth, compressing and heating surrounding material, dragging nearby matter toward it gravitationally, and in all likelihood creating a violent path through the crust. It would not neatly tunnel like a drill bit. It would rip through the local environment by force of concentrated mass and extreme pressure. Rock and metal around it would be heated, shattered, and displaced. The event would not look like dropping a very heavy object. It would look more like introducing a tiny but absurdly massive intruder into a planet that is unprepared to negotiate terms. Something else follows from that. People often assume a very dense, compact object dropped on Earth would simply keep falling to the centre and then stop there, as though the planet were a sort of cosmic bowl and the object a misplaced marble. In truth, the path would be much messier. It might overshoot, oscillate, lose energy to interaction with surrounding matter, and create repeated episodes of extreme heating and structural disruption. The Earth would not enjoy the experience, nor would anything living on its surface. A hand-sized neutron star lump would not just be a problem for the person holding it, it would be a planetary incident. And this is still under the generous fantasy that the sample somehow stays neutron star matter. Because in the more realistic version, the story becomes different, though not reassuring. Neutron star matter is stable in a neutron star because the whole star presses on itself with immense gravity. Remove a piece from that environment, and the forces that helped maintain its state are no longer there in the same way. The matter would not simply sit on a tray, behaving like a more compact kind of metal. It would attempt to expand and reorganize into more familiar forms of matter, because the extreme compression would no longer be supported externally. In other words, nature would try to undo the stellar packing job. That decompression would not be gentle. It would involve a huge release of energy as matter moved from an extraordinarily compressed state into something much less compressed. The exact details are complicated, and no one is running this experiment in a basement with a clipboard, but the broad principle is sound. Matter forced into neutron star densities owes its state to enormous pressure. Take that pressure away and the matter has every reason to stop being neutron star matter. It would not remain a neat little bead on a tabletop. It would expand violently, likely blasting itself apart into more conventional particles and nuclei, while releasing extraordinary energy in the process. So in one version of the thought experiment, the object remains compact and becomes a tiny gravitational catastrophe. In the other, more physically honest version, the object cannot remain what it was and becomes a decompression catastrophe. Neither outcome supports the phrase "hold in your hand" with much enthusiasm. There is a curious lesson hiding here. When we first began asking about the heaviest object that could fit in your hand, we were thinking in terms of weight as something passive. An object has mass. Earth pulls downward, you try to lift. Simple. By the time neutron star matter arrives, weight has become active. Gravity is no longer just something the object suffers from. It is something the object contributes in a major way. The lump does not merely weigh a lot. It alters the behaviour of nearby matter through its own concentrated mass. That is a very different category of object. It is one thing to struggle with a suitcase. It is another thing entirely for the suitcase to begin reorganizing the room through local gravity. There is also the issue of heat and energy release from interaction with ordinary matter. Whether the neutron star sample remained compact or rapidly decompressed, nearby matter would be in for a punishing encounter. In the compact case, as it tore into the Earth or crashed through structures, huge amounts of energy would be transferred through impact, compression, and friction-like processes. In the decompression case, the energy would be released because matter was abandoning its impossible state. Either way, this is not an object you place carefully on a digital scale to settle a friendly argument. It is an object that immediately turns the setting into a physics demonstration with unacceptable collateral damage. And yet the strangest part may be that neutron stars themselves exist quite happily, in the cosmic sense, without all this melodrama spilling across the galaxy at every moment. That is because a neutron star is a complete object in equilibrium. Its matter is where it belongs, under the conditions that created it. The problem appears only when the human imagination tries to isolate a tiny sample and relocate it into our ordinary environment. The universe has no objection to neutron star matter in a neutron star. It objects very strongly to the idea of you putting some in a lunchbox. This is why neutron stars are such effective teachers. They show that matter is not defined by composition alone, but by condition. The same universe that allows hydrogen, iron, water, and bone to exist under ordinary conditions also allows matter compressed into a neutron star under stellar collapse. But those are not interchangeable settings. You cannot casually move matter from one regime to the other and expect polite behaviour. Context is part of the thing, pressure is part of the thing, gravity is part of the thing. Remove the context and you may no longer have the same matter at all. It is worth pausing here to appreciate just how completely the original hand-sized question has been answered by now, at least in spirit. A hand-sized neutron star object would either remain compact and devastate its surroundings through extraordinary concentrated mass and gravity, or it would fail to remain in that state and release enormous energy while expanding into more ordinary forms. In neither case do we get anything resembling a usable object. We get a reminder that density, once pushed far enough, stops being a property of materials and becomes a property of cosmic remnants. And still, astonishingly, neutron star matter is not the final stop. It feels like it ought to be. Matter beyond atoms, beyond white dwarfs, beyond any reasonable analogy to ordinary substance. Surely that is the limit. But it is not. There remains one more threshold, and it is the harshest one of all. If enough mass is compressed into a small enough region, then the question ceases to be about what kind of matter can resist collapse. At that point, resistance itself loses. Gravity no longer settles for rearranging matter into more severe forms. Gravity wins outright. The object crosses into the regime where escape becomes impossible even for light. That is the moment when our original question stops asking about the densest matter you could imagine fitting in your hand and starts asking something even stranger. What happens when density becomes so extreme that matter is no longer really the main story at all, and the smallest possible answer is not a star remnant but a black hole? Up to this point, matter has been putting up a very determined fight. That is really the hidden structure of the entire story so far. We began with ordinary substances on Earth, where atoms hold their shape and materials behave in the familiar ways that let us build tables, ships, kettles, and all the other useful objects that keep daily life from becoming unnecessarily dramatic. Then we moved into the denser metals, where atoms are packed more efficiently, and the same small volume can carry a surprising amount of mass. After that came the first real surrender, when ordinary atoms were squeezed so hard that their familiar structure could no longer survive, giving us white dwarf matter. Then came the second surrender, where even that arrangement gave way and matter entered the neutron star regime. At every stage, gravity pressed inward, and matter found a new way to push back. That pattern matters because it tells us what the real question has become. We're no longer asking how dense matter can get in the everyday sense. We're asking how long matter can keep resisting collapse at all. So far, the answer has been remarkably long. Matter has hidden more options inside itself than common sense would ever have guessed. First chemistry, then quantum pressure from crowded electrons, then the behaviour of neutron-rich matter under incredible compression. It is an impressive set of defences, but there is a point where those defences stop being enough. There is a point where density ceases to be mainly a story about matter, packing itself into tighter arrangements, and becomes a story about gravity winning the argument outright. That is the threshold we have now reached. When density becomes gravity's victory, the object in question is no longer just a more extreme material. It is no longer a new kind of star remnant still held up by some deeper level of physical resistance. Instead, collapse continues far enough that there is no stable surface left in the ordinary sense. No final pressure state that can stop the inward pull. The result is a black hole. This is the moment in the story where people often feel the need to slow down, and rightly so, because black holes have a way of arriving in conversation already wrapped in myth. They are famous, they are dramatic. They are often spoken of as cosmic vacuum cleaners, universe-eating monsters, or holes in reality, all of which are understandable attempts to make them vivid, but none of which is quite the real thing. A black hole is not a hole punched through space like a torn piece of fabric. It is not an opening into some guaranteed science fiction corridor. It is what happens when enough mass is compressed into a small enough region that the escape speed from that region exceeds the speed of light. Once that condition is met, the boundary around it becomes what we call the event horizon. Cross that boundary moving inward and there is no path back out to the wider universe. That may sound like a very abrupt transition, but in a sense it is the cleanest one yet. White dwarf matter still says matter is resisting. Neutron star matter still says matter is resisting. A black hole says resistance has failed. Gravity has compressed the mass past the point where any known pressure can maintain an ordinary object. What remains is not a denser and denser ball of matter in the simple way we have been picturing earlier stages. What remains is a region where gravity has become so dominant that ordinary descriptions based on surfaces, materials and support begin to break down. There is something almost severe about that simplicity. Matter fought through several rounds and then, at last, gravity stopped negotiating. This is why the title of this part matters so much. Density becomes gravity's victory, not because density itself is a force, but because increasing density intensifies the role of gravity. Take the same amount of mass and spread it out over a vast region, and gravity near the edge may be manageable. Compress that same mass into a much smaller volume, and gravity at the boundary grows stronger. Compress it further still, and eventually you cross a line beyond which not even light can escape. At that moment, the issue is no longer what kind of matter is inside. The issue is that the mass has been packed tightly enough for gravity to take complete control of the situation. That last point is subtle, but important. When people first hear about black holes, they often imagine them as being made of some special black hole material, some final mysterious substance more compact than neutron star matter. But that is not really the best way to think about it. A black hole is defined not by a new ordinary material state in the way a white dwarf or neutron star is, but by the formation of an event horizon. It is a gravitational condition. However complicated the interior may be, however incomplete our understanding becomes there, the key fact from the outside is that the mass has collapsed within a region so small that escape is cut off. This is where our original hand-sized question starts becoming very sharp. Up to now, we have still been able to imagine matter as matter, however exotic. A hand-sized sample of white dwarf matter would be catastrophic. A hand-sized sample of neutron star matter would be even worse, either as a compact gravitational disaster or as a violently decompressing one. But when we move into black hole territory, the question changes again. We're no longer asking how much matter could be squeezed into a hand-sized object before it becomes absurd. We're asking what happens when the amount of mass packed into that small space becomes enough that there is no ordinary object left to hold, only a black hole of roughly that size. That step depends on a simple relationship. The more mass you compress, the larger the event horizon needed to enclose it. For stellar mass black holes, the size of the event horizon is measured in kilometers. For supermassive black holes, it can be enormous, larger than entire planetary orbits. But the same logic works in the other direction too. If you ask for a black hole small enough to fit in your hand, then you're also asking for a black hole whose mass is much smaller than that of a star, though still far beyond anything that would make the word hold sound practical. Before we go there directly, it helps to appreciate why neutron stars mark the final ordinary stop. A neutron star is already one of the most compact stable objects the universe allows, while still letting us talk about a surface and matter pressure in a recognizable way. That is what makes it so important. It is matter pushing back almost as hard as matter can. And yet, even neutron star matter has a limit. If the collapsed remnant is too massive, neutron pressure and the related interactions cannot support it against gravity forever. The exact details involve complicated physics and depend on the internal behavior of matter under those extreme conditions, but the broad story is secure. Beyond a certain mass, there is no stable neutron star solution. Collapse continues. That continuation is one of the most sobering things in astrophysics, because there is no cheerful bounce waiting at the end. The star does not say, Well, that is enough drama for one lifetime, and settle into a firmer neutron star. If the mass is too great, there is no such resting place. Gravity wins, the core falls inward, the event horizon forms, and from the outside the object becomes a black hole. It is worth noticing how different that is from ordinary collapse. If a building collapses, it becomes rubble. If a balloon collapses, it becomes limp rubber. If a mountain erodes, it becomes smaller rocks and sand. In all of those cases, the object remains part of ordinary physical intuition. A gravitational collapse into a black hole is different. It does not merely produce a smaller version of the same object, it produces a region from which escape is impossible. That is why black holes remain so conceptually powerful. They are not just compressed objects. They are compressed objects that cross a deep causal boundary in the universe. And still, despite all that, black holes are not supernatural. They do not violate physics. They are one of its sternest consequences. General relativity, Einstein's theory of gravity, permits them very naturally once enough mass is compressed into a sufficiently small region. In that sense, a black hole is not a glitch. It is a perfectly lawful outcome of collapse taken far enough. The universe is not improvising. It is following the rules all the way to a place our intuition never had to evolve for. One of the useful ways to think about this is to compare the last stages directly. A white dwarf says, ordinary atomic structure has failed, but electron-related quantum pressure can still hold the object up. A neutron star says, that has failed too, but neutron-rich matter and its associated pressures can still hold the object up. A black hole says, there is no further pressure state available that can keep the object from collapsing within its event horizon. That progression is not only elegant, it is almost mercilessly tidy. Each step reveals another layer of what matter can do. The final step reveals what happens when matter runs out of answers. There is also a quiet shift in how we should talk about weight at this stage. Weight in the ordinary sense is no longer the central feature. If you somehow had a black hole small enough to fit inside the space of your hand, the remarkable thing would not be that it was difficult to lift. It would be that an event horizon of that size implies an enormous mass concentrated into that region. The object would have gravity strong enough to profoundly affect nearby matter, and its existence in your vicinity would be a far more important concern than whether your fingers could get underneath it. The phrase heaviest possible object that still fits in your hand now starts to sound almost quaint. The hand has become a geometric reference, nothing more. It is no longer a realistic participant. This is one reason black holes are so useful in the story. They strip away the last bit of everyday intuition and force us to admit what the question was really about all along. Not carrying strength, not practical handling, not even material science in the narrow sense. It was always about how much mass can be hidden inside a small volume before the consequences become overwhelming. Black holes are the answer when those consequences are taken to the limit. At this point, people often imagine that once a black hole exists, it must immediately begin swallowing everything around it in a dramatic frenzy. That picture needs some restraint. A black hole does not reach out with magical hunger. From far enough away, it gravitates like any other object with the same mass. If the sun were somehow replaced by a black hole of the same mass, the planets would still orbit in broadly the same way, though life would have other complaints. The black hole matters because of how much mass is concentrated in a small space, and because of what happens once you get close enough, not because it is a cosmic vacuum cleaner with emotional needs. This becomes important when we eventually imagine a very small black hole. Its danger does not come from theatrical appetite. It comes from the concentrated gravity near it, and the fact that crossing the event horizon is a one-way event. There is another useful correction here too. The phrase black hole sometimes makes people picture a region of perfect emptiness, a literal hole. But from the outside, a black hole is defined by mass, gravity, and horizon, not by being empty in the everyday sense. It is a region where our standard descriptions of what is happening inside become deeply limited. We can talk clearly about the mass, the spin if it has one, the charge if it has any meaningful net charge, and the horizon. We become much less confident when trying to describe the interior in familiar terms. That uncertainty is not a failure of physics so much as a sign that our best current frameworks are being pushed hard there. For our purposes, though, we do not need to step across the horizon. It is enough to understand what the formation of one means. It means that density has crossed from extreme matter into gravitational confinement. It means the old question about what matter is made of has been overtaken by a new question, about whether escape is possible. It means gravity has stopped asking matter to reorganize itself more tightly, and instead imposed a condition from which there is no outward return. If that sounds a little stark for a calm evening discussion, there is at least something satisfying about how clean the logic is. We did not leap from lead bricks to black holes by way of melodrama. We followed a simple chain. Small things can be heavier than they look because density varies. The densest ordinary materials are still just the beginning. Compress atoms too far and ordinary matter fails. Compress further and white dwarf matter appears. Further still, and neutron star matter takes over. Beyond that, no stable matter state can hold back collapse. Gravity wins. The black hole is not an interruption of the story. It is the endpoint of the same story. And yet, that endpoint creates a new beginning for our original question, because now we can ask something very specific. If a black hole is what you get when enough mass is packed into a small enough region, then what is the smallest black hole that would still fit in your hand? Not the smallest black hole the universe could in principle permit under all imaginable conditions, but the smallest one whose event horizon would still be large enough to count as hand-sized in any normal sense. That is where the question becomes delightfully concrete again, because once the hand is reduced to a measure of diameter rather than a practical tool, we can turn the whole thing around and ask just how much mass corresponds to a black hole that small. And the answer, when we get there, does something rather impressive. It makes even a hand-sized neutron star thought experiment look like a preliminary warning rather than the main event. There is a small twist here that makes black holes different from every other object we've considered. With metals, white dwarfs, and neutron stars, the question was always how much mass you could cram into a given volume. Black holes change the logic. Their size is tied directly to their mass. Make the black hole more massive and the event horizon gets larger. Make it less massive and the event horizon gets smaller. Chandra describes the event horizon as a boundary rather than a normal surface, and notes that for a non-spinning black hole with a mass of 10 suns, the event horizon radius is about 30 kilometers. It also says the horizon grows by about 3 kilometers for every additional solar mass. That means black holes do not let you cheat the way dense matter does. You cannot keep the size fixed and simply pour in more mass forever, while still calling it the same hand-sized object. Once you choose the size, the mass is largely chosen with it. That creates a useful correction to the title of this part. If by smallest black hole you mean smallest by diameter, then any still smaller black hole would also fit in your hand geometrically. But our larger question has always been about the heaviest thing that still fits in your hand. For black holes, those two ideas are not the same. The heaviest black hole that still fits in your hand would actually be the largest one whose event horizon still counts as hand-sized. In other words, once black holes enter the story, the hand becomes a ruler rather than a carrying tool. We're not really asking what the tiniest black hole could be. We're asking how much mass corresponds to a black hole whose event horizon is still on the scale of a human hand. That is the black hole version of our original question. Suppose then that we choose a black hole about 10 centimeters across, roughly the width of a compact object you might imagine fitting into a palm. Using the standard black hole size to mass scaling from Chandra, that gives a mass of about 5.5 Earths. If you make the horizon a bit smaller, around 8 centimeters across, the mass drops to about 4.5 Earths. If you make it more generous, around 12 centimeters across, the mass rises to about 6 2/3 Earths. Stretch the idea of hand size to 15 centimeters across, and you're already at a little more than 8 Earths. push to 20 centimeters across and you're looking at roughly 11 Earths. So the black hole answer to our original question is not a mountain, not a star, and not some mystical final material. It is a compact object with a mass measured in planets. NASA educational material provides a nice reality check on those numbers. In one example, NASA uses a black hole with a diameter of 9 centimeters and says it would contain about 5 Earth masses. In another, it describes a basketball-sized black hole about 25 centimeters across as having roughly 29 Earth masses. Those examples line up with the same scaling and show just how quickly black hole mass rises with size. Once you're talking about an event horizon that could plausibly fit in your hand, you're already deep into the territory of several Earths of mass. A larger hand gives you more room, but it also gives gravity more authority, very quickly. There is a second surprise here, and it is almost the opposite of what people first expect. A hand-sized black hole would be vastly smaller than any black hole formed by an ordinary dying star that we have actually observed. NASA says the lightest known black hole currently identified is about 3.8 times the mass of the Sun. Chandra says a 10 solar mass black hole has an event horizon radius of about 30 kilometers, so even the lightest known stellar black holes are still far too large in radius to fit in your hand. A truly hand-sized black hole would therefore not belong to the familiar stellar black hole category at all. If such an object existed naturally, it would belong to the hypothetical realm of very small or primordial black holes, rather than the normal remnants of collapsing stars. In other words, the smallest black hole you could hold is not just extreme in size, it also sits outside the class of black holes we routinely find from stellar collapse. That makes the next question unavoidable. Could you actually hold it? The honest answer is no, and not only because of the mass. A black hole does not have a normal surface in the way a stone or a metal sphere does. NASA and Chandra both emphasize that the event horizon is a boundary, not a solid shell you can knock on, so the phrase hold in your hand already begins to fail at the level of touch. There is nothing like a conventional material surface waiting there to meet your skin. More importantly, once you bring your hand near an object with several Earths of mass compressed into something smaller than an orange, the difference in gravity across the width of your hand becomes a lethal problem long before contact in any meaningful sense. NASA even uses a 9 centimeter 5 Earth mass classroom example and notes that at arm's length you would already be dead. The word hold simply does not survive that environment. It is also worth correcting another common image. NASA says black holes are not cosmic vacuum cleaners, and that from far enough away, their gravitational effects are the same as those of any other object with the same mass. That means a hand-sized black hole is not dangerous because it somehow sucks everything in by magic. It is dangerous because several Earth masses in one tiny region create extraordinary gravity nearby. Far away, a 5 Earth mass black hole would behave gravitationally like any other 5 Earth mass object. Very close up, though, the compactness changes everything. The pull grows intense over very short distances, and the tidal difference from one side of your body to the other becomes catastrophic. So the danger is not theatrical suction. It is concentrated gravity acting over human scales. This is where black holes part ways even from neutron star thought experiments. A hand-sized piece of neutron star matter was already enough to ruin the floor, the building, and quite a lot more. But neutron star matter was still matter, however exotic. It had a material identity that depended on pressure and environment. A hand-sized black hole goes one step beyond that. It is not a compact chunk of substance with a ridiculously high density in the usual sense. It is a gravitational boundary enclosing several planetary masses. The object no longer merely has gravity. Gravity is the object's defining feature. That is why this chapter sits where it does in the larger argument. It is the point where our original question no longer leads to a more extreme material, and instead leads to a more extreme triumph of gravity. A curious detail follows from that. Very tiny hypothetical black holes are expected to evaporate through Hawking radiation. and NASA notes that black holes can slowly shrink that way. Chandra adds that this radiation is expected to be extraordinarily weak, except for hypothetical black holes with masses less than that of a comet. That means a hand-sized black hole with several Earth masses would not vanish in a dramatic flash on human timescales. It would be far too massive for that sort of rapid evaporation. So if one somehow appeared near Earth, the problem would not be that it would politely disappear before doing much damage. The problem would be exactly the opposite. It would persist, and the environment would have to cope with an object containing several Earths of mass inside a region smaller than a grapefruit. At that stage, the original language of weight has become almost comically inadequate. To say the black hole would be heavy is true in the same way that saying an ocean is damp is true. The important fact is not that it would pull downward on your hand. The important fact is that several Earths of mass compressed into a hand-sized event horizon would dominate the local gravitational situation. The floor beneath it would not meaningfully support it. The room around it would not remain a room for long, and by inference from NASA's point that objects far away feel a black hole's gravity, just like they would feel any equal mass, a hand-sized black hole of 5 or more Earth masses appearing on Earth would be less a portable object and more a planetary emergency. Our world is not arranged to host several Earth masses in one palm-sized place and then continue with its afternoon. There is something almost neat about this answer, though. Once black holes enter the story, the question stops wandering. Ordinary matter gave us a long sequence of maybe a little denser, maybe stranger, maybe more compressed. Black holes end the hesitation. If it still fits in your hand, and you allow gravity to win completely, then the upper black hole answer is roughly a few Earth masses for something about the width of a palm, rising to around 10 Earth masses if you allow a larger hand-sized sphere. That is the cleanest final scale in the whole journey so far. Not because it is easy to imagine, but because the mass and size relationship is no longer negotiable in the way it was for metals or star matter. Black holes tie size to mass with stern simplicity. And yet there is one last complication that makes the whole question more interesting instead of less. A hand-sized black hole may be the neatest upper answer in terms of concentrated mass, within a hand-sized boundary, but it is also the first answer that your hand could never truly touch, because there is no ordinary surface there to touch. White dwarf matter would crush the hand. Neutron star matter would destroy the hand and the room. A hand-sized black hole removes the very idea of contact and replaces it with approach, horizon, and no return. Which means the final object in this sequence is also the first one that turns the language of holding into a kind of category mistake. By the time we get to the last step, the question is no longer just what could fit in your hand. It becomes what sort of object ends the meaning of fit, hold, and touch all at once. By the time we arrive here, the question we started with has become almost unrecognizable from the one that first seemed so simple. What is the heaviest possible object that could still fit in your hand sounded at the beginning like a tidy little puzzle. It invited thoughts of dense metals, perhaps a very serious paperweight, perhaps some piece of tungsten that would make your wrist send a written complaint. It sounded local, manageable, even slightly playful. But along the way, the question kept shedding its ordinary meaning. First we learned that small things can be heavier than they look because density varies. Then we found the densest matter we meet on Earth and saw that even the most impressive metals are still only the top end of normal atomic life. Then the atoms themselves were squeezed too far, and matter crossed into the world of white dwarfs. Then it went further still into neutron stars, where even the white dwarf arrangement fails and matter enters a state so severe that our daily language can barely keep up. And then, beyond that, gravity won completely and black holes entered the story. So now, there is one final question to settle, and it is the one hidden inside all the others. What is the last object a hand could ever touch? That sounds straightforward until you look too closely, which is generally how physics gets you. Because touch, like so many familiar things, is not quite what it feels like. When you press your hand against a table, you do not really make contact in the simple common sense way. The atoms in your skin and the atoms in the table do not merge into a cheerful little neighbourhood. Their electron structures repel one another. The sensation of touch is the body registering electromagnetic resistance. It feels like contact, and for all practical purposes it is contact, but on the deepest level it is a refusal, a controlled not quite. Matter meets matter by not letting itself be passed through. That is what touch usually is. This matters now because the farther we travelled into extreme density, the more unstable that simple idea became. A gold bar is touchable, a tungsten block is touchable. Even a very dense earthly object still behaves like a thing with a surface, a material identity, and the basic social manners of ordinary matter. You can put your hand on it, take your hand away, and complain about the weight later. White dwarf matter complicates that because although it still counts as matter, it is not something a human being could approach and examine with calm fingers and a scientific little hum of interest. The density is so extreme, the conditions so alien, that the idea of handling it already starts to sound like something that should require a waiver and a second opinion. And still, in principle, it remains matter. It has a surface. It occupies space as an object. It belongs to the category of things that can be called material. Neutron star matter takes that difficulty and turns it into final warning. A neutron star is still an object. It still has a surface in the broad physical sense. It is still matter, not merely gravity with excellent public relations. If one insisted on asking what is the last thing on this ladder that still counts as an object with a material surface, the answer would be the neutron star. That is the final stop before the story changes categories again. Beyond that lies the black hole, and a black hole does not present a normal surface to the universe. It presents a boundary. That is not the same thing. You do not touch a black hole in the ordinary sense. You cross into a region from which there is no return. That is a very different kind of bad day. So if we are being careful, the last object a hand could ever touch is not a black hole. A black hole ends the meaning of touch as a material interaction. It is the point where our old language has run out of road. The last actual object on the ladder, the last thing that still deserves to be called matter with a surface, is neutron star matter. And yet even that answer needs another layer, because there is a difference between what can be touched in principle and what can be touched by a human hand without the whole hand becoming part of a cautionary tale. A neutron star has a surface, yes, but no human hand could survive the approach, much less the contact. The gravity near a neutron star is so strong that the idea of standing on it is already absurd. The tidal effects over the length of a body, the radiation environment, the energy involved in falling toward it, all of these conspire to make touch a completely impractical verb. You do not walk up to a neutron star and place a hand upon it in the way you might touch a wall, or a tree trunk, or even a very unfortunate stove. The neutron star is the last object that still counts as touchable matter in the strict physical sense, but it is already far beyond human touch in every practical sense. It is the last object a hand could ever touch, only if the hand has been granted impossible privileges and the universe has been told to suspend its usual consequences for the sake of the demonstration. There is something almost fitting about that. Our question began with the hand because the hand is the measure most natural to us. It is where curiosity meets the world. We lift things, weigh them, turn them over, test their surfaces, judge their temperature, trust their resistance. The hand is one of our oldest scientific instruments, though it does not usually receive much credit in formal textbooks. Before scales, there was heft. Before material science, there was texture. Before laboratory protocols, there was someone picking up a stone and thinking that one is heavier than it looks. The hand is where physical intuition begins, so it feels right that the final answer should be where the hand itself stops being relevant. The story goes all the way from objects comfortably held to objects that destroy the very meaning of holding, and perhaps that is the real structure of the entire script. We started by asking how much mass could fit in a small familiar space, but what we really discovered is that size and human usefulness eventually separate. A hand-sized block of dense metal is still a hand object. A hand-sized amount of white dwarf matter is not. A hand-sized amount of neutron star matter is even less so. A hand-sized black hole removes the hand from the discussion entirely, except as a tragic measurement reference. In other words, the hand carries us only so far. Beyond that, physics continues without us. This is why the neutron star matters so much in the finale. It's the last place where matter is still recognisably matter, however brutally transformed. It still has a surface, it still has a kind of substance. It is the final object before gravity stops asking matter to rearrange itself and starts defining the whole situation through an event horizon instead. If white dwarf matter is where atoms lose their ordinary identity, neutron star matter is where matter keeps existing, but only under the sternest possible terms. After that, with a black hole, the question is no longer what the material is like at the surface, because surface itself has become the wrong concept. So in a very literal sense, the last object a hand could ever touch is a neutron star. Of course, if anyone is planning to test this, there are some scheduling concerns. The phrase "could ever touch," though, invites another reading too, and I think it is worth following because it brings the whole story into focus. It might not mean what is the final object in the chain that still has a surface. It might mean what is the final kind of thing a hand can still make sense of touching at all. In that broader human sense, the answer might actually come earlier. One could argue that the last truly hand-like interaction belongs not to neutron stars, but to the densest ordinary matter on Earth. Gold, tungsten, osmium, iridium, these still belong to the world where touch means what it has always meant. You can feel their coolness, you can weigh them honestly, you can set them down without rewriting a chapter of planetary history. White dwarf matter already leaves the practical world behind. Neutron star matter leaves it behind emphatically. The black hole erases it altogether. That is one of the quiet truths the whole journey reveals. Human scale is not just a matter of centimetres and kilograms, it is a matter of whether the world still permits normal relationships between object and body. A pebble is human scale. A bowling ball is human scale, though some wrists would prefer a little notice. A tungsten cube is still human scale. A hand-sized amount of white dwarf matter is not human scale even though it has human scale dimensions. That distinction is easy to miss, but very important. The universe can hide wildly non-human realities inside spaces that look familiar, and that is what makes density so strange. It is the great deceiver of scale. It lets something appear small, while carrying the physical seriousness of something much larger. A mountain earns your respect honestly. It is large, and you can see that it is large, and your body knows what to think before it gets there. Density is more cunning. It lets an object retain modest dimensions while becoming physically unreasonable. That is why the hand was such a good starting point. It is where size and expectation usually meet. Density turns them against each other. At the deepest level, the story we have followed is the story of matter losing freedoms one by one. Ordinary matter enjoys atoms, chemistry, spacing, familiar structures. Dense metals push those ordinary rules toward their respectable earthly limit. White dwarf matter loses the normal atom. Neutron star matter loses even the white dwarf arrangement. A black hole loses the whole game of material resistance. Each step is a simplification forced by gravity. Each step removes options. Each step packs mass into less room, until eventually the concept of an object with a touchable surface gives way to a gravitational boundary instead. And that is why this final title has a certain quiet sadness to it, even if the science itself is thrilling. The last object a hand could ever touch is really the last point at which the universe still offers matter, in a form that contact can mean anything. After that, the hand is obsolete. Touch is obsolete. Even the distinction between object and surrounding space starts to become harder to speak about in everyday language. The journey ends not because the universe has run out of wonders, but because our old words have run out of relevance. Still, there is something comforting in knowing exactly where that border lies. It lies at the neutron star. Not because a neutron star is friendly to hands, it is not, but because it is the last stop where there is still an object in the sense we instinctively mean. Beyond that, the black hole is no longer a thing you touch. It is a thing whose gravity has closed over itself so completely that touch is no longer the right category. You do not place your hand on a black hole. You enter a fatal geometry. It is all very bad for the hand and even worse for metaphors. There is another reason I like ending here. The whole question began with curiosity at the scale of a palm. It moved through chemistry, atomic structure, quantum mechanics, stellar collapse, neutron stars, and black holes. But it never really abandoned that first human gesture of weighing the world in the hand. In a way, that is one of the nicest things about physics. It lets tiny questions grow honestly into enormous ones. You do not have to begin by asking about singularities and event horizons. You can begin by holding something dense and wondering how far that idea goes. If you follow it patiently enough, it will carry you all the way to the places where matter stops behaving like matter and gravity stops pretending to share authority. That is quite a lot for one hand to start. And so, where have we ended up? The densest ordinary things on Earth still belong to the calm world of atoms and chemistry. White dwarf matter is the first place where atoms are squeezed beyond their ordinary identity. Neutron star matter is the final object with a real material surface, the last thing that could count as touchable matter before gravity takes complete control. A black hole is the next step, but not the last touchable object, because by then touch itself has ceased to be the right idea. The final answer to our title, then, is not the black hole. It is the neutron star, or more precisely the surface of neutron star matter, the last stop before the universe stops offering you an object and starts offering you a one-way boundary instead. And that leaves us with a rather pleasing conclusion to the original question. What is the heaviest possible object that could still fit in your hand? In the ordinary world, very dense metals give the first satisfying answer. In the world of extreme collapse matter, white dwarfs and neutron stars show how absurd the answer can become. In the black hole limit, the heaviest hand-sized answer becomes a compact object with the mass of planets. But that object is no longer something a hand could touch in any meaningful way. Which means that if we insist on both size and touch, if we insist not only that it fits, but that it is still an object with a surface, then the last object a hand could ever touch is not the black hole at all. It is the neutron star, the final material thing before gravity ends the usefulness of the question by winning completely. So now, dear listener, we arrive at the end of this particular journey, though perhaps not the end of the habit that started it. Somewhere near you there is probably something small and denser than it looks. A key, a mug, a paperweight, a piece of metal, a stone from a path. It belongs to the mild, civilized end of a spectrum that stretches all the way to dead stars and black holes. And that is one of the quiet joys of physics. The ordinary world is not separate from the extreme one. It is connected to it by the same rules, just lived at a gentler setting. If you found this soothing or interesting, or simply a pleasant thing to drift along with, I would be very grateful if you liked the video, maybe subscribed, and shared this sleepy little corner of science with someone else who might enjoy it. And before you settle in fully, I would love to ask once more, where are you listening from tonight? And what sort of hour has found you there? Perhaps late enough that the mind has begun to soften around the edges. Perhaps early enough that the day still feels undecided. Either way, thank you for spending this stretch of time here. Sleep well, wherever you are, and if you happen to pick up something unexpectedly heavy tomorrow, do spare a thought for the remarkable fact that the same universe that put that weight in your hand also knows how to squeeze matter until even touch has to give up.